Can I explain it to them now? ये कर दो. Hello guys, I'm Sarthak. So this is a touchless doorbell system. Like in hospitals and stuff, there are many infections people are carrying on their hands and stuff now. So we need touchless systems. So this is a touchless. It works on the principle of IR sensor. So can one of you give me your hand? Yeah. If you bring your hand at a particular distance, 1 second, it will detect that someone is there. So basically it works on the principle IR sensor we are using. So IR sensor works on the principle of infrared lights. So this white one is the transmitter and the black one is the receiver. So this is continuously transmitting IR lights. If I place an object above it, so the IR lights will be reflect back to the receiver. So when the receiver receives IR light, so it increases the current. So when the current increases, so it increases the potential across this resistor, and it gets compared with the potentiometer. So we have set a threshold value. If it goes above it, like if the current increases about a particular value, so the buzzer will buzz. So it works on this principle, yeah. Anyone can try if you want. And this is our human following autonomous robot. 1 second. So basically what this robot does, we are using an ultrasonic sensor and an IR sensor. So what ultrasonic sensor does is it calculates the distance between an object and the sensor. And IR sensor we are using for changing the direction. So I'll show you the demo. But right now we make it very heavy. So motors are not able to take that hold, but I'll show you how it's working. Yeah. And when I place my hand, it will start following me. Yeah. Right now the load is pretty high now, so it is not, the motors are not able to hold that weight. That's why it is not working that fast.
Anyone can navigate it?
Yeah, anyone. Right now we have, no, right now we have made anyone can navigate it. Authorization will take, like we can integrate RFID thing, so it will follow that RFID person only. But right now we have used just for normal purpose. Anyone can use it. Yeah. You asked from like school or college? College. Which branch?
EC.
EC only. Oh. So are you planning to take masters? Master. Okay. Best of luck for gate and stuff. Alright. तुम एक्सप्लेन कर दो तुम्हारा प्रोजेक्ट. हाँ.
It to be stolen by some unauthorized user. So how I have modeled it is, if I lock my system, right now the LED, the vibration sensor is sensing all the vibrations because there is a lot of vibration in the room. Wait. First I'll put my system in the lock state and my red LED would be on. Okay. So now my system is in lock state. Suppose if any unauthorized user comes and try to vibrate this entire system, the buzzer will keep on buzzing until someone who has this authorized tag come and tap on it. So since I have the unlocked tag, so I will tap the card and my buzzer went off and my green LED glowed. So my system got unlocked. So basically it is just the anti-theft detection box. Yeah, that's it.
इसमें बोलना होगा ना,
जब डेमोन्स्ट्रेशन दिखाएगा मतलब माइक पे जाएगी
डेमोन्स्ट्रेशन देते देते बोलूँगा तो अच्छा लगेगा भाई.
तेरी इच्छा.
So this is basically a Li-Fi based audio transmitter. So as you see, this is I am speaking through the mic, and this my audio is transmitting via the light, and it is going to the speaker. So the entire transmission is occurring through the light. If I block the light, nothing is coming out of the speaker, and if I release the light, it is going. Basically what we are doing is modulating the amplitude of the laser light using the electrical signal that is the mic is producing. So this is basically a Li-Fi based product. So we are basically demonstrating how a very simple thing can implement such a huge thing. Like this Li-Fi based system is implemented very widely. You can see it in airplanes, you can see it in medical devices like normal RF signals. RF signals in our day-to-day lives we use everything gadgets. These RF signals might interfere. For us, the normal people, it does not matter much. But for the people in airplane or the military purpose or in medical use, the interference might cause very hazardous things. So these visible Li-Fi based things are used. And because it is light based, the speed is extensive. You can take this transmitter 1 kilometer, 2 kilometer far. If you can focus the laser here, it will transmit with zero latency. And as you can see, the audio is also very crisp. So like it can also be, we can encrypt the message and we can also transmit. Like it is widely used that way also. Yes. So this is our project and this is our demo.
For the camera only, explain. Okay. Hi, I'll start. What happens is we collect the context of the data and only the context is transmitted. So for example, this is an event-based communication we are showing. Here you can see in the scene, there is a raw video of a horse grazing in a field. So instead of sending this complete data, video data, we are identifying horse in the image and we are generating the text for this image, and only that context is been sent to the other side. So the receiver receives this context and displays that horse is grazing peacefully in a field. Okay, so only few bits are transmitted instead of the whole video. And on the receiver side, we are generating an audio, textual, and video and image descriptions on the side. So based on the event, we generate a scenario, context, and only that context is transmitted instead of the whole data. Sorry? Cut, okay.
It has to go inside. It's also fine. There. It's also okay. Open this button.
Localization. So here we are explaining Bluetooth 6 localization, where we'll be using channel sounding methods of Bluetooth 6 to identify the distance between the two objects. So let's say I'm in a living room and I want to find something in a dining area. So I'll place this anchor node in the dining area and place all these anchor nodes wherever in the home, and this has a range of up to 150 meters. So as I move away from the object, the distance is increasing. So here we use three methods like IFFT, phase and RTT. So in phase-based ranging and IFFT, we use phase slope to calculate distances. And using RTT, we use timestamps to collect the data, and using such multiple nodes, we find the distances. And this has up to a sub 10 centimeter accuracy.
No, give it on. He will explain.
Not generic or technical? Yeah. Generic only, no? I look at. So our project is data transfer app. So this project basically has the ability to offload a humongous amount of data, which is, for example, in this project we have taken mall as an environment. So this humongous amount of data is divided into particular chunks of 100 MB based on the data itself, and it is offloaded to the user or the visitors that are data mules for us. So this is done by an app which is installed in their device. So this data will be offloaded to the different users in form of chunks, and it will be uploaded to the main server once they have exited the mall, and they can upload this from anywhere in their home or in some public Wi-Fi, and anywhere they can upload. And this data will be then offloaded to the main server, where it will be stored permanently. After the data is stored permanently in this server, the files which have been downloaded in the main server will be then deleted by the server in the mall. That's our project. Yeah.
This prototype of glasses, smart glasses, which can be used to translate Indian Sign Language. Okay, so what it is going, basically the setup is, we have a camera, we have this camera, right? It is going to take images of whatever I am showing in front of it. Once that is done, the controller inside this is going to translate all those images, access the model that we have trained, and it is going to run the object detection model, and it is going to show which sign it has actually translated into. So if I am showing 4 like this, this is 4 for Indian Sign Language. If I show this, then it is going to detect 4, like gesture detected 4, and is going to show the confidence level. Once that is done, in the setup what is happening is, this is the OLED, it is going to display this, but here it is going to display a mirror image of it. What actually happens is, it will pass through the lens and it will show the converged form over this screen. This reflective screen basically will the gesture which is detected, it will directly appear in front of your eyes. So instead of checking the screen or something else, you can directly see it. And this whole system is real time. You can see, I'll play the video for you. Yeah, you can see right now it is showing O. Once I change the gesture, so now I have changed the gesture to 4, right? Once that is detected, the camera, the OLED on real time will display the translation. See, it was 4 initially, so now it is detecting 4. Now I'm going to change it to O, and then it is going to again change it to O on the OLED itself. So basically this is just the prototype. In sign language there are 2 types of signs. One is static gesture and other is dynamic gesture. So these 4 and O, these are all static gestures. But if I am doing a sign like this means help in Indian Sign Language. So if I do this, that is a dynamic gesture, and this model that is right now running, that can also be trained for that as well. So you can basically improvise on that. Instead of just sign language, you can even apply your own model for something else as well. So it's basically customizable, smart glasses which can be customizable according to you.
You take only 2 signs only?
Yeah, right now this is just a prototype. We are checking if it can actually work or not, if it's feasible or not. Now we have trained it for 4, just 2 signs. We can add more models as well. No, wait.
of LED. So because of our eyes, we can't differentiate. So if you rotate it, then you will be able to see as if it is a 2D thing. You can see the letters coming on it because of persistence of vision. The concept is persistence of vision. Because of our eyes, they can't differentiate it between them. Okay, that's it. Okay. This is the power supply. Yeah, I am giving 3.7 volts to the DC motor. As if I will increase, then the speed will also increase. But these letters will not be stable anymore then. Okay, that's it. Okay.
So to explain, no? You come and explain. 1 minute.
So how do you hold this? Like this? Yeah. 1 minute.
How do we do asynchronous tracking? So basically this is a neuromorphic camera and we are simulating a blob which is moving from a slow to a high speed. So if you capture this sort of a scenario using a conventional camera, then you will get motion blur. So you won't be able to localize exactly where the blob is. But in a neuromorphic camera, you get events in the form of XYPT. So now because of its high speed, you can actually cluster the events and do the blob detection as well as tracking. So in this particular demo, as you can see, when the blob is moving, we are able to cluster that there is a single blob, and this particular visualization over here is, so this blue dot that you see is actually the blob, and you are able to track in real time, and these are the X and Y centroids which are getting updated with time. So this is a single blob which is getting tracked. So in our experiment, we are able to track a blob moving at 17,000 pixels per second, which is a very high speed, without losing the tracking of the blob.
Arun bro.
Hello, so today we are going to demonstrate Coherer effect. So Coherer means actually coherence of particles. So here these loose balls represent loose bit of metal particles which have high resistance between them because they are dispersed. Now here we have a battery, and with the help of the battery we have connected it to the set of loose balls and then an LED. So as you can see, the balls are touching each other, so you would expect the LED to glow, right? But that is not happening because there is high resistance between them, because these are loosely packed. So what we're going to do is we're going to use this candle lighter and we're going to generate electromagnetic field. We're going to use this piece of metal as antenna, and you can see that the LED is glowing. So what happened here is when we use this antenna to send the electromagnetic field over here, the loose set of particles form micro welds, and there is a conductive path between them to conduct now. And you can disturb the field very easily by just clapping or just blowing some air. Thank you. This was what was used in olden day telegraph systems. So you can see the Coherer device here. It used to consist of a glass tube with loose metal particles, and this antenna was for receiving the radio waves. So whenever the radio waves hit this piece of device, the metal foils here start conducting and the bell used to ring. This was what was used in early day radio systems. Thank you.
Yeah, okay. So what we have done is an FPGA-based brick breaker game. So we have written every code in hardware to mimic the older retro game thing. So this is the gameplay we could show.
So we're using UI to take an input from a keyboard, and this game we are just using as a giant FSM.
So everything is like hard coded into the FPGA. So these loading screens and the U lose and the victory screens and all are added in the VRAM of the FPGA. So for the block generation, it's every time random. So we have used the linear feedback shift register to make it like a random generation every time. And all the ball physics are like coded to be like a minimal style, and that's it. So for the resource utilization, we could show you this thing. Like the LUT count is around like 3% only, and the F flip-flops used are like less than 1% of the total. And we could see the on-chip power to be almost very close to 0.2 watts. Yeah, that's it. Yeah, that's done.
preparing the slide, we are also sending the images to the pathologists. So all of this like significantly reduces our time. And our prototype also reduces the cost because a microscope commercially it is like almost a few lakhs, like 20 lakhs, 25 lakhs. But our prototype is bringing down the cost to almost 1/20th of the entire cost that is commercially available. So it becomes readily available and affordable for all kinds of people. So like this is it. By using this, you can just like move up and down and see. Like
use your phone as a screen.
Yeah, and then this is like for, see it is going out on focus. So like for bringing it in focus. This is like our initial stage of the prototype. Our next stage of the prototype is going to be completely automated, where you would not even require a joystick. So everything is like you don't have to control anything for focusing. Also, everything will be completely automated.
One more prototype we have. So this is for the doctors. When you are doing when you are removing the breast cancer, so you basically want to way to see the breast cancer. In surgeries, you cannot differentiate normal cells from cancerous cells. So what we are doing here is this albumin is a protein which is already present in the blood, and then ICG is a dye. So when we inject this dye into our blood, these combine form this albumin plus ICG. And what happens is when we shine infrared light on it, we can it reflects it back and we can see the mixture. See, look here.
See, only the one which is mixed with albumin and ICG glows, and you cannot see the rest of it. So albumin is already present in our blood. When we inject this dye called ICG, it gets plotted in and around our cancerous blood cells. So like using this camera, the doctor can see in real time where those blood cells are, those cancerous cells are actually. So and it becomes easier for him during the surgery.
Any questions you guys have? Okay.
Can we say that the result what we get here is unsure?
and low power applications where we need to detect the events. What's our main selling point is this whole setup is ultra high speed while using a very low power. So we're integrating our own custom accelerator known as Homi in this while leveraging the sparsity of this event camera. The main thing of the Homi is we using a Raman core, which is our own indigenous developed accelerator, which is utilizing the sparsity and leveraging this sparsity in saving the computations. While the normal computation using simple multiplications, we'll just skip those multiplications which is not required if the events are 0. So finally, we're increasing the throughput to roughly estimated to 1000 plus FPS we're reaching with the 5 watts of power usage. So as you can see, for this current applications, we are using the gestures. We are training this using DVS datasets. The person is just clapping and only the events are being captured and is being recognized using the accelerators. So that's what we have built. This is a lighter version of MobileNet, but it's a custom-made MobileNet. I have 16,000 parameters. It's using depth-wise convolution layers.
Or else any other, the working of these, the capturing of the data?
So capturing is basing work on the DVS cameras and the backend is being worked on the convolution models. So this is our Homi, which we are leveraging the perception task. What in this we are doing is we are leveraging the sparsity of the event camera. Event camera basically captures only the sparse sparse event. If there's some event is being happening, it only captures the overall event. Now we'll leverage these events into the Homi accelerator. With this accelerator, we accelerate the task of classifications and detections. It is based on a Raman accelerator. The Raman accelerator is different from the conventional accelerator in such a way that we are leveraging only the sparsity of the network. In convolution, every number is multiplied with every number, so the convolution always takes place. But in this Raman accelerator, we are skipping those convolutions which is not being necessary. So in truth, we are increasing the throughput while maintaining the accuracy. All the setup is coming around roughly around 5 watts while achieving 1000 plus FPS. So this is what we have built. So this application lies in detections in drones. It could be used in defense where low power need is required while running on the battery operated devices. Thank you.
Okay, so like I said, I am someone who uses sign language. You cannot understand sign language, okay? So what you can do, you can just put up these glasses. Whatever signs I will do in front of this camera, it is going to take all the, capture all the images. It is going to give it to the controller. That controller has an ML model deployed over it. That ML model will do the live translation of that gesture. So you can see this is the O. If I'm showing this in front of this camera, it is going to show O. And if I'm going to show this gesture, it is going to show 4 with this kind of confidence level. So what is happening, you can see here, right? Right now it is showing O. Okay. Suppose if I'm changing the gesture, skip it to that. Yeah. Yeah. So you can see, once I'm doing that 4, it is now showing you 4 on the O. The setup is in such a way that right now you can see the, like clearly you can see here, right? Inside this has the OLED. There is an OLED inside it. You can see it here. It's attached to it. Yeah. So the OLED is basically displaying the mirror image of it. That mirror image is going to pass through the Fresnel lenses. It is going to converge and show it displayed directly over here. Like it's going to project that image over here. So directly you can see it in front of your eyes. And it is, the setup is like very comfortable for your eyes. So you don't have to strain it. You can just directly see it. And then we can add even more, like the entire model can be customized. So if I want to add more gestures, I can do that as well. Now these two are just static gestures, right? I can add more gestures like dynamic gestures. So suppose if I'm like doing this gesture, this is for help in Indian Sign Language. So even that it will translate and show you directly. So in real time you can do that. So suppose there's an emergency situation, like there's a person coming in the emergency section of the hospital. That person, the doctor can just wear these glasses if that person doesn't know Indian Sign Language, and he can directly know what that person is saying and will be able to help that person better. So in emergency situations, these can be used. Even in situations where there is, customer support you need in a market or something. If that person is using Indian Sign Language and you don't know that, so you can just put up these glasses and it will like give you live translation for that.
So when you're making this project, what are the crucial things you face to make it?
Okay, so you see this camera, right? This camera is not the, this is a third-party camera. It's not directly connected to the Raspberry Pi. So you need to figure that out, how to connect the third-party cameras and all, because there are some commands you run, right? Those commands might sometimes show that camera is not detected. So you need to figure that out as well. Even the models, right now it is showing 80%, right? Earlier when we were training it, we realized that we will basically need like thousands of images just to get this much accuracy. Earlier it would show just 1% or like 40% or something. For if I'm showing O, it would have shown me 4. So the crucial part is model training. And model training usually requires like thousands of images. Just for this one O, if you want to you need to basically select this frame, right? And people have different hands as well, hand sizes, hand colors and everything. So that model needs to know that even if the color of my hand is changing, it is still O. Even if I'm doing slightly like this, but I still mean O, right? So it needs to know that even this is O, even this is O, and even this is O. And we are using RoboFlow for this. So you can set, you can basically set the augmentations for it. You can say, you can change the color. This is a monochrome camera, so it's not capturing color images. So you can train that, but on RoboFlow, you can also say if the color is changing. It is capturing black and white images, but if the color is changing, even that can, that is going to give you this accuracy of at least over 70%.
So this percentage gives us the accuracy of what?
Yeah, the confidence level. So ML models basically give you, bias. There are biases and there are weights and everything, right? This is basically showing you the confidence level. So if it is O is being detected, the model is 80% confident that O is being detected. Like that.
The screen, this is LCD.
Yeah. So this is the OLED actually. This is the reflective screen. This is, you can find it over, like you said, you can find it over LCD screens and stuff. This is a reflective surface. It's highly reflective. So whatever will be displayed here, that will be reverted and you can see it directly over here.
You're displaying it here and then that reflects itself.
Yeah. You can see it. Like Meta Ray-Ban, but they are using these hand bands, right? Wristbands. So those are detecting electric.
They had some ray glasses.
Yeah, glasses only they had, but it comes with the hand band. So it is basically detecting all these electrical impulses from your hand. Exactly. But instead, this is directly taking it from the camera and then doing the translation instead of putting it on your hand.
What's inside all this?
So this is the space for battery. Right now we haven't connected to the power supply, and this has the controller inside it. See, you can see in the images this is connected to the controller, this is connected to the band and all, right? So this band is going to the controller that is here. Do you want to see what's inside? Yeah, Raspberry Pi 0 to W we have used. It is connected to the Raspberry Pi, that is connected to the OLED, and then it's a simple setup, just 3 components, and then it will be reflected over here.
Coding you have?
Sorry?
Coding.
Yeah.
What kind of coding you have?
So we are basically using Python. We are running the script. So I'm using a Python script. Do you want to see the code?
He won't understand.
No, wait. So what happens? You can see this, right? Python camera capture.py. Right? The moment I run this code, that code has all the IP address and everything, right? It is going to access that RoboFlow model that I told you about. That has the ML model. That is what we use for training. It is going to access that. That will run all these images, check the confidence level, match it with the already existing objects inside it, and then it will send it back to here, the controller. That controller will send all that data to the OLED, and that will be displayed.
Any drawbacks in this? Like, you feel that we can improve it more?
We can definitely improve it more. Like, these are just 2 gestures, right? We can train it, we can add more gestures. We can also try to sort of reduce the delay. Right now what we are doing, it is directly accessing the whole model over the internet. What we can do is we can deploy it locally. So we won't even need to run this code. I can just switch this on, I can introduce buttons over it, I can just switch it on and it will directly start translating. Right now I have to run this code, but then if I deploy it locally, then I won't have to do that. Just switch it on, like the other IoT devices that we have, right? They don't need to you don't need to run a particular code. Suppose on the phone you have this application that open the curtains. You can just click that and the curtains will open. You don't need to run this code and run this Python code and then it will start working. You don't need to do that. So we can improve it according to that as well. We can try changing the camera. We can do, instead of a monochrome camera, we can use a RGB camera. That's it.
Any chance we can make the camera as a small camera, minimize
We can definitely do that. So this is just a prototype, like a TRL 2-3 level, right? Technology readiness level. TRL is technology readiness level. This is just the prototype and it's on a very lower level. You can increase this, you can reduce the battery size. This one, I think is it visible? Yeah, you can see this is the battery. This is the battery management system. That is connected. This is a 3.7 volt battery. So you can do that. This is going to provide whatever is needed to you, right? And then you can basically reduce the battery size. That's one improvement. You can reduce the camera size, like you said. That's also improvement we can do. Instead of having this one big camera, you can just have one that is small, very small.
So the whole model is custom 3D printed.
Yeah. This is so this guy is responsible for that. He does all the 3D printing and everything. He knows how to take the dimensions and do everything. He has printed it for us.
How are you sending that? Is there a screen over here?
Yeah. So the OLED that you saw. Yeah. So the OLED that you saw is inside. Yeah. Yeah. You can hold it. You can see it.
You see the OLED is inside. So that's reflecting here, okay? That is reflecting here like this.
So that you can see the screen.
That OLED, that is displaying a mirror image. This is a Fresnel lens. It will converge it and display it on project it directly over it.
What was the overall cost for it?
Overall cost, I think it went to 3,000-4,000.
Basically, it shows only the numbering or alphabets also mentioned.
So we can train it for alphabets also.
Yeah. So it will be more, it will be more easier to understand.
Exactly. So right now the only alphabet we are showing is O because we don't have that much time right now. But we can add more, the entire alphabet we can add.
Thank you so much.
Yeah, thank you. Thank you for coming.
Hello, this is a demo on accelerated NP-hard optimization with Neuromorphic icing machine. So I will start with a very interesting problem, but that happens very regularly in real scenario. Let's take an IPL fixture. So there are now 10 teams and 80 different matches in the group league that has to be organized. So you have 80, so you have 80 factorial different ways in which you can decide the fixture. Now 80 factorial probably sums up about 10 to the power 100 or 10 to the power 120, something around that range. So if you do a classical von Neumann computing in classical CPU with step-by-step algorithm, sequential processing, it will take thousands of years to reach the most optimal fixture that will minimize your traveling cost, total number of distance, and the total carbon emission. That is most important, right? So that is not possible. So here in this case what we are doing is we are trying to map this problem into a physics-inspired algorithm. So here we call this an icing machine. So in this icing model, if we okay, ये इधर दिख नहीं रहा है ना इधर. Okay, okay.
Explain is a movement is here. Okay.
Yes. Okay.
Energy.
Okay. Okay.
Potential is a.
This is an demo on accelerated NP-hard optimization with neuromorphic icing machine. So I will start with a interesting problem. So let's say you have an IPL fixture which has 80 different matches that has to be scheduled. So in what way you can decide the fixture so that that will optimize the total carbon emission, travel, cost, and everything. So for this, if you use a normal CPU with sequential von Neumann computing with step-by-step algorithm and sequential processing, it will take thousands of years to reach to the minimum fixture that will optimize your total cost and everything. So here we map this problem with a physics-inspired icing machine, where we map our problem into this optimization function, and this icing machine inspired from this magnetic ferromagnetic coupling of dipoles to reach to the optimal minimum. So here our optimization function is the total distance once you decide the fixture. So here this algorithm we deploy on this hardware, on this classical FPGA hardware. So here we are using a quantum inspired algorithm which gives probabilistic computing and convergence to a minima, a CMOS hardware that gives scalability, a high speed, and most importantly room temperature operation, no need of cryogenics. And we also use a neuromorphic architecture that gives parallelism and event-based compute at a very low power. So if you see here, this is the entire solution space where this is exploding. So these are multiple neurons that are firing, that is showing here. And this is the energy landscape. If you can see this black dot, that is reaching the minima somewhere probabilistically. So it searches random spaces and finally reaches the minima, that is the global minima, at least in this space. So this is the initial location of the cities for which we need to decide the optimal fixture, and this is the computation that is happening in this FPGA in real time. So it took some 30 milliseconds to reach to the final result, and this is the final fixture, and this is showing the intermediate results. And this is not limited to only this kind of problems. These are very wide industry problems in logistics, machine learning, to VLSI, drug design, and FPGA mapping. Yes.
It can come from here. Okay. So which has many sensors, like you can see camera is also there, like IMU sensor is also one among them. So it has accelerometer and gyrometer, two sensors, which will detect your motion, acceleration and rotation speed. So we collected that accelerometer and gyrometer readings for these 10 activities, and we tied to your wrist and did all these activities and collected the data samples. And we used those data samples to train a machine learning model. We used the decision tree model to train the model. And finally, we deployed that model in that device, which has 1 MB RAM, a storage space. So now it will classify and detect what we do. Based on our hand vibrations, it will classify and show what I do here. So yes, like suppose if I do phone interaction, this is also activity I trained. So this small vibrations also it will pick and show there properly. And if I stand, it will take 3-second latency is there. I kept, and it will show I'm standing. It will take some time. Standing like this. And if I do jogging, it will show jogging. It will detect the hand movements. Like walking also. I don't, okay. Walking also it will show like that. And this is something called pick and place. We trained for picking an object and placing it in another place. And this is eating with spoon. Trained for all these activities. So it will do multi-class classification. So thank you. Huh? You can train for the activities which will help in parenting and all, like so what and all activities which should be like
Child is wearing this one.
Yeah, you can see like what how it is okay or what type of activities. And if it falls down, you can get some you can child care and all. Range it will come from that end to this till this door is there, no? So around 50 meters it will come. Inside home, all over you can a medium-sized home. Throughout the home it will keep connected only. If it's green color LED, it's connected like that. Home to school, you can use Wi-Fi or some other medium to transfer the data, upload online, and you can do no problem. Then also you can do. Yeah, now but we are using the same Wi-Fi to connect it, so now we can do in this length. But if you want such long distances, you can upload to online cloud, and you can be anywhere in the state, and you can access from there. So no problem. So that was you can do. Huh? Okay, thank you so much.
Should we wait for people? Good morning. This is Bluetooth-based localization. So you all must have used Google Maps, right? So we cannot go out without Google Maps. But what if you are inside an airport or inside a mall? You will not find the directions easily. So you have to find a map and then do it. So this indoor localization is a hard problem all over the world. We are trying to solve it using this Bluetooth Low Energy 6, which is the latest BLE standard. We have two nodes here. One is the reflector and the initiator. Reflector is the person moving around, trying to navigate. And initiators are multiple anchor nodes that should be placed all around the walls. Okay, so we have three methods. So first, we have to find out the distance where they are to localize them. We have three methods. One is using fast Fourier transform, phase loop, and round trip time. we have fast Fourier transform, we have phase-based changing. So based on how the beacons move and using phase differences and all, we'll calculate this phase load. And round trip time is nothing but the time of light. Yeah. And now you can see as the person with this tag moves, the distance is also increasing. Now we know how far the object, but we don't know where exactly it is. So to get to the coordinates, we will have multiple anchor nodes. Here we have anchor 1, 2, 3. Yeah. And using the intersection of all the three distances, we will be able to accurately locate the person. If we have multiple anchor nodes, the accuracy will improve.
So this is our IR sensor module. Okay. So we are using infrared lights, right? Okay. Infrared sensor. So it is continuously transmitting IR lights, which we cannot see through naked eyes. So this is receiver. Okay. Whenever we place an object, you can place your hand. Anyone can place your hand. Yeah. So the lights are getting reflected from your hands and getting received at the receiver. So when it gets received, the current increases through this branch. When current increases through this branch, the voltage increase at this point. Okay. When voltage increases, it gets compared through an comparator, LM358 comparator. And we have set a threshold using potentiometer. Okay. So whenever the voltage is greater than the threshold value, it will
So this is an RFID based anti-theft detection box. What it does is, let's consider it is some of my valuable lab equipment and I don't want it to be stolen by anyone. But if someone unauthorized person tries to move it, the vibration sensor would sense those vibrations and it would make the buzzer on and on. The buzzer would keep on buzzing until someone who is the authorized person comes and tap the card to unlock the system. So this is my RFID reader. These are two tags. For this card, I have put it its ID as so that this can lock the system. Its ID is, I am using its ID to unlock my system, and this is to lock, sorry. So now my system is in the locked state, but if someone tries to move it, the vibration sensor would sense the vibrations. You can do some vibrations. Yeah. Now the buzzer would keep on buzzing. Since you don't have that authorized tag, you won't be able to make the buzzer off. So it is a theft detection thing. But this is the card. This would unlock the system. You can tap, buzzer would go off, and the system is now unlocked. Yeah. This is the RFID reader. These are the two tags. I've modeled it in such a way that this is I'm using to lock the system and this is to unlock the system. You can use one tag. This is Arduino Nano. This is a vibration sensor. This is the buzzer. This is the reader, and these two are the tags for it. Yeah. Each tag has a unique ID. So like you cannot use any other RFID card to tap on here. This would work only for these two cards only. Because this has a unique ID, this has a unique ID.
Keep any other ID?
No, it won't work because this is sensing only its ID. If I keep my RFID card here, this won't sense the ID here. Like
what it shows actually?
In my screen, it would show that wrong RFID card.
If you get the wrong ID,
yeah,
what?
Buzzer would keep on buzzing. Like now the buzzer is buzzing. For unlocking the system, I have fed it its ID. But suppose if I use this, buzzer won't go off. Yeah, this is the right ID. Now the buzzer would go off. That's how it's.
Instead of buzzing, is there any other way that you get notified?
Yeah, I can add some more IoT components to it so that I can get a notification on my phone. Yeah, that would be more advanced. Like this is the basic thing, buzzer thing. We can expand it more by integrating more IoT stuff.
you are in 8th standard, you might not know C language. So there's a program for C language. So what basically will happen is, suppose there is a password of, suppose your first character was 7, right? You get 7. You can see there's a 7 printed there. So first character was 7. So suppose there's 7 here, okay, and there are all the letters here, small a, small b, small c. It will compare a with 7. If it matches, it will stay there. It will go to the next character. If it doesn't match, it will exit the loop again. So that happening of extra instruction will cause the power leakage. I'll give you an example now. Okay. So what I'll do is I'll send the 2 wrong characters. I'll not send your password. I'll send wrong. Okay. I'll send yes and I'll send 1 byte, that is 1. Okay. If I run, you can check there's no difference in the power trace. It is same. Basically, it is overlap. Now I'll send your character that is 7, right? So if I send 7, you can see there's a difference in the waveform, right? That extra instruction is causing a power leak. That power leak we are calculating and we are guessing a password. That's all. So main idea is to understand the side channel analysis. Okay. So side channel analysis is basically, the side channel attack is basically, you're not changing anything in hardware, you're not changing anything much in firmware, you're getting the power, you're getting the password only through the power. So there are 3 types: power analysis, timing analysis, and electromagnetic analysis. But here we are doing timing analysis. Through the power trace, we are getting a timing. You understood? Little bit also? Got it, right? So you can think this as of a password machine. Okay, if you enter the correct password, then only some box will unlock. So if I know the power of that machine, I can guess the password correctly. Got it? So that is all. That's all explained.
So here we are. We have made a 2D metaverse.
It's a browser-based virtual space
where you can interact with each other, and as you can see in the screen, we two are close to each other, so we can see our screens simultaneously.
So visitors can join either through a QR code. There are 2 kinds of different multiplayer rooms in it. One is a private lobby, which is password protected, and one is a public lobby.
And also if we want to use the whiteboard, so simultaneously we can see each other's ideas and we can draw real time and convey through each other. Okay, so we can convey through each other. If you can see in the screen,
yes,
and I draw it in real time, you can speak to each other and share ideas.
There is also a computer section here where we can present our screens in real time, and we can conduct lab meetings also. So there is a proximity detector between 2 characters. When 2 avatars come in nearby, their webcams get on and they can interact in a live way. So I can show you that. So 2 characters को पास ले ज़रा. So there is this one character Aryaman and other is Sayantan. So if both of these 2 characters come in close by, so this webcam gets on. So there is a proximity detector also.
Exactly.
You can share the screen also in the computer section area.
This is basically
virtual space for conducting lab meetings. There are endless possibilities basically.
So this is an
which
idea
my
phase.
friends
We can
explain.
deploy it in either companies or we can replace teams through it.
और screen section दिखाना और screen section दिखा देना explain.
So what happens is, here we leverage a quantum mechanical phenomena called as coherent population trapping. Now cesium has got this special property where you shine two radiations on cesium separated by a certain frequency. That frequency is this number, 9.192 gigahertz. So what happens is, we expect some absorption, right? So if you keep a detector post cesium, you should see a decrement in the detected signal that you detect. But what happens? Something very interesting happens. There will be an increment in the detected signal. So ideally, according to our intuition, if it absorbs light, what should happen? This should reduce. This is the detected signal. You keep a photodetector after your cesium and then measure the output. There should be a decrement, but that doesn't happen. There will be an increment, and this is very much dependent on frequency. So there is resonance there. So as an electronics engineer, if you ensure that you provide this frequency to cesium, you are always there at the maximum. And then all that you have to do is to lock to this maximum by making a negative feedback. By ensuring that, you'll always get a very stable frequency. So this is a typical negative feedback system where we use a mathematical term called as Allen deviation to characterize the clock stability. Now the red plot that you're seeing here is a very, not a very good oscillator. It's a free running oscillator. You take an oscillator, you measure its frequency over time, and then you compute this mathematical term called as Allen deviation. You estimate it. When you plot it against time, you have this kind of a dependence, where initially it reduces and then increases again. But the moment you put this in negative feedback, your resonance, which is a quantum mechanical phenomena, improves the stability of the clock. In a way, the stability of your CPT is being transferred to the oscillator. Yes. All these boards were fabricated here, designed here. And we have built this atomic clock in our lab, Q Classic lab. And the stability is almost 10 power minus 10. Any doubts, any questions?
This can be minimized. The ideal goal of this project is to minimize it in chips.
It's a controller, it's a microcontroller. So basically you have to implement a set of algorithms for temperature control, for wavelength control, and also to lock the frequency to this maximum. The controller does that. Same microcontroller, it's a different microcontroller.
These are different types.
Yeah. So this is used for temperature control and this is used for wavelength control. And this is an oscillator board. So what happens, we'll have jumper cables connecting this board to this one. All these pin headers that you see here. The controller will update a certain digital code. Now you have a digital signal, you want an analog signal out of it. What do you need in between? You need a DAC. A DAC does that job. Those DAC and the other circuits are there on this board.
So here we are using ESP32 module for car and a controller. In both we are using ESP32 module, where it is having a Bluetooth module. So this joystick and these are push buttons. From here we are sending a Bluetooth signals, which converts Bluetooth signal into PWM, and this PWM converts to drive these motors we need a driver circuit. So everything was built in this PCB. So based on the PWM it will rotate the speed. So if for left and right, so one side of the car will rotate in the forward direction and one side of the car will rotate in the backward direction. So it's a simple game. So you need to solve the maze using the car and a controller. Thank you.
It's fine. Yeah. మళ్ళీ ఒకసారి ఎక్స్ప్లెయిన్ చేస్తా అంటే వీడియో రికార్డింగ్. Actually this is a gesture control car. So here is IMS sensor and transmitter module. Based on the position in which direction it is facing, it will send the data through this transmitter module, and the same module is placed here for reception, and based on the received data it will give commands to the motors in which direction it need to move. So based on that it will work. So this is basically a gesture control car. ఇలా ఉంటుంది.
Yeah, sure. So it's a project, it's basically a storage platform, 6 platform, which has basically, you can move any orientation. So on this, we're basically using 3 different scripts. A Python script which has media pipe running, which can basically gesture control. We identify the exact movement of your palms and convert those into XY coordinates, and this is sending that exact thing into your processing software, which is simulating the storage platform digitally. Okay, and that storage platform digital software is basically calculating all the servo angles which the server has to move to make the platform move in the exact same orientation as the platform. Okay, so whatever XY coordinates is retrieving from the Python script, is then converting that into a stator, and that simulation is finding the servo angles for each of those servo motors, and the servo angles are then fed to the ESP32 via this cable, and then this USB32 is just converting, sending those signals to the motors. Okay. So yeah, so now if you want to just try it out, you just put your hand up, bring it in the middle. Yeah, now up, down, keep your hand straight. Up, down, left, right, solve the maze. Keep it straight. Up, down, left, right, above. Yeah, I'll just show you a demo. So let's bring it first. Up, down, left or right, and you go diagonal also. Try it out.
Which language?
Middle first.
Which language? Python?
So it has Python, C++, and embedded C.
Okay. For
Python script is basically Python script is basically just doing your gesture recognition and finding
process.
Yes, it's using a media pipe library, which is finding the XY coordinates for the palm orientation. And XY coordinates is being converted to your pitch and roll. So up and down your x-axis, y-axis is your pitch, x is your roll.
Yes.
Okay, and those angles are then sent to your simulator. So it's the simulation of the entire thing.
By Blender?
No, it's a software called processing.
What?
Processing. Actually.
By Java?
No, it's C. Sorry, Java. So you just move your hand. It is exactly finding the exact angles for the each servo motor. So your pitch and roll is being fed to a platform, and that's a kinetics program calculation done in the background. Inverse kinetics, which will find the exact servo angles required. And those servo angles being fed via the USB cable to the ESP32, and then those just setting the servo angles for each.
Which microcontroller are you using?
ESP32.
What?
ESP32.
Arduino?
No, ESP32. It's a separate thing. ESP. You want to try?
Thank you.
Pardon?
Thank you.
Do you want to try?
No.
Fine. Who wanted firmware? Who wanted firmware?
Yeah, hi, my name is Seja, and we optimized a pick and place robot to draw artistic things. Usually it is optimized for picking and placing industrial things, but it has a good thing about thing is it has a 0.5 mm precision. So we thought we could use that 0.5 mm precision and map the images in XY plane using the 0.5 mm precision and gliding through the XY coordinates so that the pen will glide through the same XY coordinates and draw the images something like this. And these are the specimens we've tried already. And we are, since the image is converted to XY coordinates now, there is another issue that the robot actually moves very slow. So we use traveling salesman problem, something like when we have the coordinates around the plane, we are optimizing it to draw very quickly, like moving to the nearest first, rather than moving to the farther. That's how we are achieving a good time limit, and we are fixing the z-axis to the same plane as the paper so that it won't move and up and down, and we are just gliding through the XY plane. And we are also using the conversion algorithm as that Gaussian blur and phase contours thing, so that we will get a smoothen out images.
In normal traditional games, you will be having only one generator and one discriminator. Here you will be having two generators and two discriminators. Generator wants to fool the discriminator by creating a fake image. Discriminator will try to identify whether it's real or fake. So here the horse image is transformed to zebra, and zebra is again transformed back to horse. So the zebra, the original details will be preserved. Like the original horse and the reconstructed horse will be almost similar. There will be no much differences in this. So in real time, we can use it for deblurring the images. Like for medical scans, you will be having like MRI scans. You can deblur the images. And during traffic light simulations also, like if you capture the vehicle number plates, you can deblur the images like that. We can use it. And here the main motto is we will be transforming the images which have no paired data. So that's why it's called as unpaired image to image translation. Thank you.
Is it on? Okay, so myself Akash, and today I have developed a robot. Its name is Saras. So what Saras can do? Suppose first I am explaining what is Saras stands for. Saras is basically a smart autonomous robotic assistant system. I derived this name from goddess Saraswati. So what he can do, he will act as your personal assistant. He will assist you what is in front of him. He will communicate you, like whatever you have questions, he will reply you. Whenever you will say, hey Saras, explore the environment, it will explore the environment, and whatever comes in his front, he will stop there.
trigger his camera. Camera will take a picture, and after picture, the picture will go to the LLM model, and the LLM model will describe what he has seen. After seeing this, what he is making a log file there, and in that log file, he is keeping all the information that on this coordinate I have seen this object on that coordinate in this direction. Let me show you the interface. See this is my lab's coordinates grid I have made. So you are seeing that stars here. Here the stars are indicating the object he has seen during the exploration. So see, suppose this is a grid A, grid B, and there will be a grid C. So we will go grid C, what he has seen in grid C. So grid C. So he has seen a metal bowl directly there in grid C. So what we will do after exploration, we will say, hey Saras, go to metal bowl directly. He will go there because he is seeing, he is logging everything what he has seen. See, while exploration, he was in west direction. He is seeing in west direction. He is keeping the coordinates here, and this is a 25 grids in that area. So he's covered all 25 by 25. He detected 47 things, and here is the activity. Whatever you are asking him, whatever you are saying him, he is keeping all the informations here. This is the battery. I'm using two batteries here. One battery is powering a Raspberry Pi, and the other one is for motor control things. Right now it is in online mode, so that's why here saying online. Let me show you some basic tasks. See. Hey Saras, can you dance? See, what is happening is not capturing what I am saying. Let me try one more time because there is lot of noise coming here. Let me try one more time. Hey Saras, can you dance? Dance. See. He is changing his face expression according to the task. That's for all. Yeah, sure.
Bro. Yeah. This is a project called Firmware. It's a firmware extraction tool. It's built in IISc, the PCB. So it's based on a FT222 chip, which is communicates between SPI, I2C, UART, JTAG, SWD, and multiple different protocols, communication protocols. So the entire use of this tool is basically to extract any firmware once you connect to any communication pins or any other available things. So one application of this would be, suppose you have an old router. Your old routers have these things called, have these exposed EPROMs, which has the firmware for the entire router. So if you connect to this directly from this using this tool, and you run the software which we use, you can flash and you can dump the entire firmware of the router and get the original bin file. From this bin file, you can then reverse engineer the bin file using tools like Ghidra to get the actual code logic back. So once you use tools like Ghidra, the problem is the variables become randomized because it's the binary file does not know the software does not know the actual variable names. So once you convert the .bin file to actual code, you get the randomized variable names, randomized everything, but the strings will be constant. So if it's a badly written software, you'll have stuff like hard-coded login passwords. So once you convert the binary file back into the actual code, you can use those extraction tools to find strings and identify any hard-coded passwords. Another application is, once you have the .bin file and have the original code, you can write your own malicious functions like any backend access to your router and basically reflash the EEPROM. And once the router reboots, it will run normally like a normal router, but it will have your backend entrance to the entire network. So I'm a seller of routers and I go to SP Road, set up a stall, and I sell cheap routers which has my malicious code in it. And anyone buys it, it will run normally like an exact normal router, but I'll have backend access whenever I want. So it's just a way to really show that this tool can have many applications, and one could be malicious, but it also have its own good advantages also.
Should I start? Yeah, this is the ML-based hardware accelerator that I am designing. So this is the EMG sensor, electromyography sensor. What does this sensor does is, it takes the input from the users, it takes the inputs to recognize the 6 gestures. After taking the inputs, the signals are being fluid processed, and this analog signals will be converted to the digital signals. And after getting the digital signals, these digital signals are fed to the hardware accelerator. This hardware accelerator is trained on a CNN model, convolutional neural network model, and this convolutional neural network model detects. Tries to detect which of the gestures I am trying to put on. Based on these gestures, the required program will be executed. So this can be used in applications like gaming industries, healthcare centers, industrial revolutions, and everything else. Thank you.
Speak. Completed, bro. Just completed.
I am Madhumita, a first-year PhD student at the Circuits and Security Research Lab at Indian Institute of Science. Yeah, so I'm a first-year PhD student at the Circuits and Security Research Lab at IISc. So our demo is breaking classical and modern cryptography using power side channel on a chip whisperer. So every cryptographic algorithm that is designed, it is designed for the security purpose. But when it is implemented in hardware, there are unintended leakages in the form of side channels, that is in the form of power, electromagnetic radiations or timing. So this is a simple demo on how we can use power consumption to we can use the power consumption, that is the power traces, to find out what the secret key of the device is. So this is the chip whisperer setup. So we have a target microcontroller, which is an 8-bit microcontroller, which has the AES-128 being executed. We have the capture board, which captures the power traces and sends it to the PC to perform something called as a correlational power analysis or a machine learning attack in order to find the secret key of the device. So for a machine learning attack would take less than 10 traces in order to find the secret key, compared to a correlational power analysis, which would take about 2,000 traces to find out what the secret key is. So that's about this. Thank you.
Hi, I'm Samarth from CSR, and I'm here to present a demo on the security trust is leaking and mainly understanding and preventing side channel attacks. So let's say, what is a side channel to start with? So side channel is unintended physical information leakage from a system which is inevitable. That means we can't outrun from it. So let's say we are asked to design a frequency generation block, so which has some RNC that we have designed based on some formulas, but an attacker can be able to intercept this data without even trying. So even though we enclose this system as a product and put it as a black box to an external world, what happens is the power terminals are still visible to an attacker. So what happens is, let's say, ideally we have to power it on like this, but an attacker, you can use this resistor to actually supply the power from here, and you can measure this. So this point, what it will be is VDD minus IR. So this functionality of the chip will be given out by the current that is getting consumed. So to see a demonstration, now I'm just probing directly the supply directly to the IC, right? And what you're seeing is nothing but the glitches that's happening. So here, there's only glitches that is present. And now, when I change the power supply and give it through the resistor here, so you're able to see frequency related data that's coming outside, right? And this can be extended into real world attacks where you can use this design and attack can be replaced with any other cryptographic chip, and your key can be retrieved and your whole system will be compromised. And so we have also come up with a countermeasure that is tailored, which is TDC-based power supply, power side channel attacks. So what we do is mainly we try to place a TDC which is physically close to this cryptographic core, and we mainly try to compensate using reverse current. So if your crypto is consuming current in one direction, we try to mitigate it by consuming the current in the reverse direction. But ideally this isn't happening because there will always be some delay from here to here. So we do see some phase glitches coming in, but still we have implemented this in an FPGA, and using security analysis, what we can see is without the countermeasure, an attacker can get the key for an unprotected AES within 5 key traces, whereas with
protection. Then with Tyler that is used, the protection is now increased to 1,65,000, which is almost 300 times improvement in security. And I've just provided references which is of the published work here. And you can see in terms of power overheads and area overheads, Tyler is significantly better than proposed other countermeasures. Thank you.
depth estimation is
Your first name.
I'm Surekha, I'm from IISc first year. This is depth estimation using stereo vision camera. So in this we are trying to imitate human eyes, how humans can perceive depth in real life. We are trying to do it using two cameras. From the same point we are capturing two images from two different viewpoints. That is the same image but we have two different viewpoints. So the image, the objects will be somewhat differed. The pixels will be mismatched. This pixel mismatch we will calculate, we will measure horizontally and we will convert it to depth. Whatever is nearer to the cameras, it will be of more disparity, and whatever is farther from the camera, it will be of less disparity. So this we are converting to depth. From this we are color mapping this. Whatever is nearer we are trying to show it in red, and whatever is farther it is showing in blue. This is for object detection part. For that we used a CNN model. This we are trying to integrate in driving assistance systems. So it can easily identify the obstacles and it can give the commands to the driver whether there is an obstacle, we have to stop or give a brake. So this is the map. Every far object you can see in most of blue, and if you come closer to the camera, more edges will be more of red. So it's
actually if we are 0 to 3 meters, then the camera sense it. Yeah, if it is 0 to 3 meters, then the camera sends it, and the camera gives notified to the driver or the autonomous vehicle to stop or to take the diversion. And if it is beyond 3 meters, then it would be in the blue screen. You can see the blue screen, there is only the blue screen, so that the driver can be notified. So that, and we already have the LiDAR thing. Normally we are using the LiDAR as of now. The LiDAR is, there will be an interference issue with the LiDAR, and the LiDAR can't detect the small objects, like if a cat is going or the dog is going, it can't, then there might happen accidents. So avoid this, we are trying to integrate this with the LiDAR thing, so that we don't get any accidents and we will go in a correct manner. We are trying to integrate in the cars or vehicles. Yeah.
only for cars it's useful.
You can use in every vehicle, right? Other than bikes, bikes we can use it. We can use in trucks also, and even we can use in the moon, like when in a space program also. You can see the depth, how much it is. Yeah. Thank you. Yeah.
Okay, so purpose was. Okay, so today's demo is to understand side channel attacks, the basics of side channel attack, only through a power trace. Okay, so what we did is the user input a password. Okay, so we calculated, we send that password through a firmware to a hardware. Okay, that hardware computes the password, and it will leak a power. It will send a power trace through this cable. Okay, so that power trace will capture. It will look something like this. The trace will look something like this. So this is an example of power trace where when we did not send anything and we sent a letter A. Basically, random noise versus random character A. Okay, you can see there is a noticeable difference between both, because while sending A, there are some internal operations happening that will leak power. With this logic, we will try to guess the password. So you can see the password is already guessed, it was same as the password. Now we'll understand how it actually happened. So for that, we'll go to the C code once. You can check the logic of guessing the password. So secret is the password itself, and guesses are the 62 characters. 62 characters in the sense 26 small letters, 26 capital letters, and 10 digits. So when a wrong digit encounters, it will break the loop immediately. But if a correct character encounters, it will not exit the loop and it will try to guess the next character. That one guess of an extra character will cause a delay through a power trace, and it is a noticeable, and it is fairly visible. So we'll see that now. So what I'll do is, I'll keep it a little simple. Okay. So I'll send a wrong character, and both wrong characters I'll send. Okay. I'll not send your first character S, and we'll see how the trace looks. You can see the trace looks almost same, exactly same, because both the characters are wrong. So what I'll send one wrong and send one correct. Okay. You can see the delay of one instruction. It is trying to guess an extra after the first guess. It is trying to guess next. So with that logic, we'll repeat it 5 times and we'll get the password. That's the simple basics of how a timing leak happens. Basically, the main purpose of this was to understand, students should understand the side channel attack. Basically, the side channel attacks are nothing but the non-invasive attacks where we don't alter the system, we don't add anything to the system, we don't take anything from the system. Only using the power trace, by identifying the leakage or by identifying the delay, you will get the password. So that's all for the today.
Do we need every time a time delay for power leakage or just power leakage?
It can be anything. It can be based on operation also. Suppose it's not timing and you're doing two operations, or you're doing XOR and somewhere you're doing just OR, or you're doing some AND operation, you're not doing AND operation somewhere. That will also leak. So there are three types: power, timing, and electromagnetic. So today we saw power and timing. Through the power trace, we identified that there's a time delay. That is all. You understood?
Thank you.
Yeah, for now we
to balance the stick with your hand, what you just do, move your hand forward so that the stick will get balanced. In the same way, here if I am pushing this, the wheels are trying to balance it. How it is doing is, here the microcontroller is giving an immediate response. If it's not in zero, this equilibrium, it is pushing in such a way that it will come to its equilibrium position.
We have used IMU unit here, inertial measurement unit, which contains two major sensors. One is the accelerometer and one is the gyroscope. Accelerometer feeds the motors with how much input you need to give depending on the tilt angle. Tilt angle is calculated by using the gyroscope. These both are fed as feedback inputs to the microcontroller, which again calibrates it and put it back to these wheels. These are guided by these motors, stepper motors.
You can try pushing it, it won't fall.
What is the max angle it can bring?
30 degrees.
And to bring it back, there will be motors which are active?
No. Yeah, these are the motors which will bring. From the zero, it won't lift. We have to lift it manually. Once it is in the range of 30 degrees.
Yeah, you have pushed it manually, but to bring back.
That will be done by the motor.
Motors.
Yeah. It's like if you try to tilt it forward, the motor will accelerate forward so that it maintains the 0 degree.
Just you can give a small push, you can understand that something is trying to push you. Small push. Yeah, something is. Sorry. Okay.
Wait. Recalibrate.
You can see
the push which you gave it recently. This created a force which made it to move beyond 30 degrees, and it fell down.
So after 30, does it still try to correct itself, or does it just stop?
Within 30 degrees, it will try to correct whatever disturbance you have given. After 30, the motor will stop. That is how
I know it will fall, but will it stop correcting itself?
The motor will stop.
Actually, the whole object is not symmetrical. There is some wiring, so the motor will rotate some short duration every time because there is no symmetric equilibrium position for this. So there will be small rotation in this motor.
So it can be used for bikers who fall while biking?
We can use it for skateboards actually, hoverboards or skateboards where people will fall from the skateboard because they won't have some equilibrium position, so they will fall. In that
Actually,
you can use.
by using such type of robots and all, we can explore the combination of how embedded systems and control systems work together. We can explore its possibilities. Yeah,
PID
good
controller.
catch. Thank you. Good catch.
Thank you.
PID controller.
What programming languages you use?
C programming.
C. Have gyro?
Yeah, gyroscope and accelerometer.
This is the gyro.
This is the gyro, this is the controller.
Controller. Which one?
This one. Texas Instruments TIVA microcontroller.
You can see in this video actually, like initially it's not able to get balanced, but once the microcontroller is on, there is some feedback mechanism which is trying to balance it.
And to tell you, you must be wondering how did we calculate the KP, KI, and K. Can you guess?
I mean, it changes based on the values of the sensor, right?
Yeah, and how did we assign those particular values to the sensor?
Maybe you assign some angle to the 90 degree and then the angle
You're
deviates.
absolutely correct. We gave some random measurements. Based on that, we calculated some fixed values. And we calculated KP, KI, and KD.
Which one is this thing? Microcontroller?
TIVA
microcontroller.
TIVA.
And some of them they dissolve the mantle or the crust like this. So now the last thing that I want to show you here, an experiment is going on. In the video you can see it is trying to set up this experiment again for live, but also we have captured it because it takes billions of years of time in the real situation on our mantle. So what happens? The mantle is liquid, but there is compositional difference, and also there are volatiles in the mantle. So due to the change in volatiles and due to the change in composition, there is a density difference. And what happens if two invisible liquid of different density, they are kept together? The lighter one will try to come up, right? This is why the red one, which has a slightly lesser density than the clear liquid, that will try to come out, and we call it.
While it will be coming up, the process we call is the mantle plume. Okay, and these mantle plumes, they come up and they pierce through the upper crust and form a volcano. This is the easiest way you can visualize and understand the formation of volcanoes. There are tons of other ways in which a volcano can be formed, but this is the easiest way to understand. Now, this kind of, it is not showing here. Okay, fine. Now, as we know, our crust is divided into certain plates and the plate tectonics, and these plates moves, right? So these plates moves and the mantle plume is coming up. So what will happen? One volcano will be there, and then while next generation of plume will come, back then the plate will move forward. So another volcano will form. Then for the third session, another mountain will form, right? So there will be a series of volcanic islands, because if they are in the interplate region inside the ocean, so we will find them as islands. The Hawaiian volcanic chains that we call is a famous example for this. But what happens if there is no plate tectonics at all, but the mantle plume is coming? What will happen? Any guess? Mantle plume is coming, but there is no plate tectonics. So simple. As mantle plume is coming generation after generation, but plate is not moving, yes, this will pile up, one over another. This will pile up. And exactly this is the case for our neighboring planet Mars. How? Because Mars has no plate tectonics since a way back in time. It has plate tectonics in past, but now the dynamo of the Martian dynamo is almost almost ceased. And so that when a mantle plume comes up, it piles up and piles up so high, you can see the highest mountain in Mars, that is the Olympus Mons. It's not only the highest mountain of Mars only, it is the highest mountain all over the solar system. whereas the highest mountain here we found on Earth is only 9 kilometers. Okay, so it 3 times taller than that. So because of the non-ability of the plate tectonics, it goes up. And there are other issues and with the yes, there is no atmosphere and there is a very less gravity to pull the thing down, also this. But on that point, I may leave you to giving you after giving you a general idea of this study. That is one. We can show it to the other. Done. So I will guide you to the next table where they are showing some interesting minerals that these rocks are formed, the comprises of this mineral, and inside there is another library of minerals and other aspects of the department that what we do. Thank you all for coming. नेक्स्ट बोलने के बाद
इधर एक इधर से लेना है
but only one can do all those things. If you find a better angle, you just separate. So it is just mic.
কখন খুলবো স্ক্রিনটা কখন খুলবো ওখানে ওই ক্যামেরাতে করতে হবে নাকি কাকে বলবো Welcome to Center for Earth Sciences. So what we do here is we basically try to understand the Earth's processes by physics, chemistry and mathematics. So first order interpretation and data analysis comes from the rocks. We try to understand the story of the rocks and minerals because we know that the rocks and minerals, they have their own story to tell. So these are granites, these are basalts and these are andesites. All of these 5 rocks, they are igneous rocks. And these are the most abundant igneous rocks in the continental landmass, and they are dominated by silicon and potash feldspar, silica oxide and potash feldspar. And These basalts, they are dominated by FeMg group of elements. Because of the presence of iron and magnesium, they contains a color, they are quite darker. And this group of rocks, which are andesites or diorites, they are somewhere lying in between these two end members. This is one peculiar rock which it looks like quite similar with these granitic rocks, but they have a compositional differences. Like these rocks are rich in terms of sodium, calcium and silica, whereas these rocks are rich in silica and potassium. But the interesting part of this rock is, this is the dominant rock of lunar highlands. The brighter parts of the moon that we see shining white or shining yellow is because of the presence of these rocks. Whereas the darker parts, the dark spots in the moon, they are actually of basalts, which are these group of rocks. And this is also another type of basalt which is known as giant plagioclase basalts. They are actually, these samples are actually collected from Deccan Troughs, and all of these are igneous group of rocks. Now once these igneous rocks, they come into the surface, the superficial processes come into picture, and rivers, winds, glacier, they actually break these rocks, they erode them and try to bring those eroded materials into some other places. So when those eroded parts are carried mechanically and deposited mechanically in somewhere else, they form sandstone or shale group of rocks. This is a sandstone. These are all sedimentary rocks. But if those eroded or weathered materials, they are coming in a form of solution, they are coming in the form of dissolved state, and somewhere they precipitate from a chemical solution, this simply makes a chemically precipitated sedimentary rock like limestone or banded iron formation. Both of these rocks are formed under the sea at the ocean floors, and this is a fossilized limestone. Limestone means calcium carbonate, but these parts are some of the broken fragments of different organisms, whereas this is a banded iron formation, and the possible age of these group of rocks is around 2.4, 2.3 billion years. This group of rocks, they actually bears the evidence of first global oxidation event. What do I mean by that is, the initial Earth was not having any free oxygen in the atmosphere, but around 2.5 billion years ago, the first set of oxygen-rich atmosphere came, because of which iron plus 2 transform into iron plus 3, and iron plus 3 gets easily precipitated from any kind of hydrothermal solutions, particularly here in under the sea. And alternatively, when the reducing environment prevails, the silica-rich red parts are deposited. The red is actually because of presence of some iron dusts within the silica-rich layer, whereas the grey color is actually hematite-rich band in this banded iron formation. So these are the sedimentary rocks. These all are sedimentary rocks. These are of igneous rocks. Now most of these igneous rocks, they are actually formed at the plate boundaries. Plate boundaries means these are the plate boundaries. These are the divergent plate boundaries, and where the plates are separating away from each other. All those red marked regions are the divergent plate boundaries. Whereas these blue colored regions, they are the subduction zones, where the plates are going or sinking into the interior of the earth. So these rocks are normally found in those two places, but here are some intraplate volcanic activities. That means those places which are within the interior part of the plates, but they are still showing some volcanic activities or rigorous volcanic activities. So in the next part, we tried to just simplify the mechanism of melting in this interior part of the plates. So we used two different types of liquids. Basically, we try to replicate the mantle solids, which is rising from the core mantle boundary, which is actually around a depth of 2,900 kilometers, from where a solid, buoyant, hot mantle material is coming and rising up to the surface. But because of the time constraint, we cannot use two solids, and so we just tried to maintain the density contrast and use two liquids here. And we will just try to demonstrate you how exactly the mantle plume comes up from the core mantle boundary up to the surface. So he will show you. So this is how a rising mantle plume looks like under the surface. And this is the exact mechanism how the Deccan volcanic provinces are formed and how these volcanic island chains, ocean island chains are actually formed. These are Hawaiian chains of volcanism. And how the chains are actually forming is the plume source is constant in the at a depth of 3000 kilometers. And the Pacific plate is moving northwest in this direction. Now the plume source is constant at here, and the first, the Pacific plate is moving. The first set of magmatism is coming here. Magmatic activity is done. Then it crossed here. The magmatic activity is now going on here. In this way, there are several pulses of magmatic activity, and a chain of volcanic island is forming, and that is exactly present here. So this is how, in a dynamic planet like Earth, the system goes. But on the other hand, if we talk about the Mars, the plate tectonism is not there. The plate tectonism is not there. So if you look at the maximum heights or the maximum elevations in our planet that has around 8,000 feet, 8,000 meters in Himalayas, but the Olympus Mons that has a much more height compared to what we see in our planet. These are the height of in the order of 25 to 27 kilometers. The reason is because this is a stagnant planet, the Mars is a stagnant planet, so there is no plate tectonic activities. So the plume source is continuously feeding something from the bottom and constantly throughout the millions of years, and materials are basically piling up there to form a igneous volcano with this much of height. At the same time, Mars doesn't have this the significant quantity of atmosphere which would be responsible for weathering, but as it is not there. So the weathering process is also very less prominent in Mars, because of which the height is so much high. Done. And these are also some other rocks. These are actually the mantle rocks, danites and paidotites. And this one is a metamorphic rock. This one is a metamorphic mineral. This and this one. This is garnet. This is kyanite. And this is also a metamorphic mineral, aluminosilicate. This is sillimanite. And this is kyanite. So, and these are some of the meteoric samples. These are extraterrestrial samples. That means those samples that are coming outside from the Earth. These are chondrites, and these are iron meteorites. These might be chondrites or stony meteorites. These are the two end members. So these are silica-rich materials, and these are iron nickel rich titanium iron nickel materials. So if you compare the density, you easily understand that these are extremely heavy compared to this. But this actually forms the core of a planet. This gives us an idea about the core, and this gives us an idea about the bulk silicate part of a planet, of a differentiated planet. And here we just take a video from NASA. Then we tried to show you how exactly the sample collection is thought to be done by the Voyagers or some probes on the surface of the Mars. So this is all. I'm done.
Thank you.
Thank you.
Yeah, so there's a variety of minerals you're seeing out here. See, everybody is distinct from each other. Some does look a bit lame, some looks fancy, some look well shaped. Okay, you can hold on to it. See how well shaped they are. This one. And then we have some which are not so very in good shape. Okay. So what in nature we find is, we find a different type of shapes and colors. Okay. And it all depends on its genesis. So these two minerals that you're seeing are the same minerals, exactly the same. Okay. But you can definitely tell some differences out here. Color difference, yes. Shape, numbers. See how many crystals we have here? A lot of crystals. And look at how beautifully they are shaped. The crystal size is big and the shape is also pretty much well defined, right? So this is something we have tried to recreate in our lab, keeping in mind what's the process behind it. Okay. Now these two is what we have created in our lab. Okay. Now if you take a look at this, you can hold it too. Again, what's the first observation is? Small, lot of crystals, and see how irregular those crystals are. See, they are tiny and all, right? Yeah, the crystals are light. And then we see this one. So this is a one single crystal, but it has slightly a better shape and bit bigger too. So what happens when magma comes towards the surface? Okay, it starts crystallizing because the temperature is reducing, right? So if the rate of cooling is very fast, it doesn't get time to crystallize and grow well. So it will try to quickly crystallize as much as it possible, and it will form a bunch of crystals with small and irregular shapes. But then we have some magma that will slowly come upward, and it will grow, it will have enough time to grow, and it will have a very low cooling rate, right? Then it will create these beautiful crystals. So this has taken millions of years to grow. That's why it has made such a beautiful crystal. This is not cut by any human. It is naturally found exactly like this.
These are from different places.
These are from different places. So this is a fluorite. This is a calcium fluoride mineral. Okay. Now I can compare, show you this. Like this is a calcite. See, these two are same. Absolutely same. Calcite. We have not cut it. It's natural. Yes. Now you can definitely tell some difference. See how clear it is. So the growth rate of this crystal is fantastic, right? At least better than this. Still it's good. You can see some shape, right? It is worth getting. But this is much better. And these minerals have a very distinct feature. I will ask you to hold it, and you can just keep it into the crosshair. Can you see a difference?
Double arrow.
You can twist it also. Just rotate it. Slowly, slowly, slowly you can rotate it. You definitely see some difference, like it was rotating. So have you studied refraction? What is refraction?
This is artificial.
No, that's reflection. Refraction. Bending of light?
Bending of light.
Right? So why does it happen? Because the speed of light changes the moment it enters a medium. But we don't see splitting of light, right? So these minerals are anisotropic in nature. Okay? So the physical properties of a mineral changes along different direction. Okay? So the moment light enters, the speed of light changes in one direction than the other. That's why we see one line in two separately. So this phenomena is called double refraction. Simple, right? I can just keep it here. So take a guess what this is. It looks like a metal block.
Can you make any guess? What could be?
It looks precious at least, right? It has a metallic color like a silverish, a bit of gold. It definitely is not a cheap thing, and it has a very beautiful structures, right?
It's a rock, basically.
Just figure it out. It's a mineral.
It looks like iron.
Yeah, yes, iron. And it's quite heavy too. So can I get it? Yeah, thanks. So this is called a fool's gold.
Fool's gold.
Yes, because it is deceptive, right? So sometimes people just look at it, oh, it's very precious, it's heavy, yeah, it will cost some bucks, great. But unfortunately, that's not the case. So this is iron sulfide mineral or pyrite, okay? Now, usually sulfides are blackish in nature, okay? Does it look black in any direction by any means? No, it doesn't, right? So if I just scratch it, now you see a black color. So that's a straight giveaway, that it has to be anything but gold. So that's how the name has been come. And you do have some idea about these minerals? Haven't you heard of amethyst? No. Yeah, so it's very commonly used in jewelry. People do wear it in their rings. Okay? Yes? The same thing goes for.
Can you just repeat
Yeah.
that's the name, mineral name?
Amethyst.
Amethyst.
Yes. So it's just quartz. Simple as that. But during its genesis, a bit of iron incorporated into it, giving it a distinct color. For this thing, same process, but this time a titanium gets into it. Again, a very trace amount of titanium has entered it. The moment it enters it, the color changes, the value changes. Because the normal quartz doesn't look this fancy, right? And then again, if I compare this one, see, this is green, right? Now this has been caused because of a crystal defect. That's why the color is coming. So imperfections are increasing the values of these rods, right? Okay? Okay? Oh, I've shown you this one. So what is this? Fish. It's a fish. So it's an imprint of fish. Okay? We can't have the fish in a whole fish. We can't have it, right? Because
we have the impression, the structure of the fish imprinted on a soft sediment.
Yeah. So why? Because for a very long time, what will happen? The fish will degrade. The entire fish will be gone, but the imprint has been kept. But then sometimes, like this. Okay. Any guess? It looks very similar. This is a fossil too, but it does look like a wood.
Yeah, actually.
Yes. So this is called a petrified wood. It's heavy. Wood is not very heavy. So what happened is it has become a rock in itself. Okay. Or the sediments have they entered into the pore spaces and they have formed a rock in itself. That's why it's so heavy than a normal. So what happened is sometimes some fossils, some early living beings get buried. Okay. And they are getting cut off from the atmosphere. So we know that oxygen is the main parameter that degrades everything. So the moment it gets buried very quickly, we can protect it from oxygen. So little bit of degradation will happen because of bacteria and all, but still we can preserve a lot amount of it, especially the hardest stuff. That's why we have the bones of dinosaurs, not the flesh of it. But then again, we have some evidences of woolly mammoths. You may have come across, right? They got frozen and they are in glaciers, they found in glaciers. The flesh is also preserved. So the key is that any fossil that you get, you may find in impressions, okay, and yes, and the ones which we get, like the physical fossils. Now the fish doesn't have harder stuff. The bones are also very fragile, but things like wood or bones, they are very strong and they can resist for millions of years. So that's why we get it in nature. Okay? Thank you.
Thank you.
Hi. So you're seeing a lot of
Geophysical inversion lab. We are recording of the by the different and these are the seismograms that you see here. These are the recordings done at these seismic stations. And this is the vertical section of the cross section of the earth. So here you can see there are different layers like crust. So since crust is very, very thin as compared to the radius of the earth, so we cannot see here, but here we have mantle, outer core and the inner core. So these differentiations are based on the composition, different compositions. So higher dense material settles down and the lesser denses are more closer to the surface. So this is how the waves propagate during the earthquake. So the recorders, that is the seismometer that detects these seismic signals, these are those seismometers that are placed at different seismic station to record. So this can basically detect. This is a 3 detect up, down, south. So this is to record, and this is all about the earthquake. So earthquake So we are from the Geophysical inversion lab. We are demonstrating here how the recording of the earthquakes takes place by the different sensors. So here we see that this is the region that is representing where the earthquake takes place. So that is representing different kinds of wave. That is here P wave, S wave, and when it propagates inside the earth, the different kinds of seismic phases it generates, depending on where it gets reflected or refracted, and it gets recorded at the different seismic stations which are present throughout the globe. And these red triangles are representing the different seismic stations. This P and S, these are the body waves, and this you can see here, the yellow one, these are representing the surface waves. And these are the seismograms that you see here. These are the recordings done at these seismic stations. And this is the vertical section of the cross-section of the earth. So here you can see there are different layers, like crust. So since crust is very, very thin as compared to the radius of the earth, so we cannot see here, but here we have mantle, outer core, and the inner core. So these differentiations are based on the composition, different compositions. So higher dense material settles down and the lesser denses are more closer to the surface. So this is how the waves propagate during the earthquake. So the recorders, that is the seismometer that detects these seismic signals, these are those seismometers that are placed at different seismic station to record. So this can basically detect. This is a 3-component recording. So it can detect up, down motion, east, west, and north, south. So this is to detect, and this is to record and generate those kind of seismograms. So this is all about the earthquake. So earthquake produces huge amount of energy that can penetrate inside the earth, and we can get this deeper information. But if you want to analysis like the shallower part, then we can also generate seismic waves. Not only we can rely on the earthquake also always, but we also have a hammer. So by hitting a hammer on the ground, we can generate seismic waves, and these waves propagate inside the earth, and when it reaches to the geophones, there we record the signals. So you can think of this geophone as analogous to this red triangle that I showed. So if anyone hits the hammer, if he hits the hammer, so you can see these wiggles are coming. So this is how the recording takes place. And if it is more closer to one geophone, so there you can see the energy will be high. So again, you can see this kind of. So this 1, 2, 3, these are representing the different number of geophones. So this one is representing closer to us. And if, again, can you? So here somewhere he has, these are the signatures of hammer, and he has just thumped with his feet. So these are the different signals that we are observing. So what is happening here, when he hits the ground, the waves propagate and recorded by the geophone. So actually in geophone, what is taking place? The mechanical energy is converting into electrical energy. So in that, there is a coil and the magnet. So because of the ground motion, there is a relative motion in it, and the electrical signal gets generated. It passes through this wire, and it gets here. It gets, so this is the geode, and it converts the electrical signal in these sorts of different seismic traces. And these, by studying these seismic traces, we can study what is the nature of the source and what is the ground condition. So the signature of these seismic traces depend on that. If instead of hammer, if someone jumps or run, the signature of the seismic trace going to change. And also if we change the ground condition, then also it is going to change.
It's only surface waves, no? What is it?
Yeah.
Surface waves, okay.
This nearest will experience more.
Yeah, so the nearest waves,
Then farthest will
yeah, you can see the lowest.
Soil nature also.
Yes, soil nature also.
How you detect the epicenter basically?
So for epicentral distance, so this is called the active seismic that we use for the underground studies like construction site, or this we can use for the detection of the basement record and all those things.
But seismograph won't help you to get the epicenter, no?
Yeah, no. Like here we can see, you talk about epicentral. So for in order to detect epicenter, we need at least 3 stations to do that. So we need, we know the velocity of P waves. Yeah, so this circular thing, and where those 3 circles intersect, we detect on the base of that. And also like P wave is faster than S wave. So the farther you are,
Because of that only we come to know the discontinuity in the internal part.
yeah. So these different phases help to understand deeper part of the Earth.
So I think that was the important evidence that we come to know about internal of the
Yeah, so
seismic wave, right?
yeah, so the seismic waves helps a lot because this is the only wave that can give the magnified image of the Earth and up to that much deeper part.
ZPR uses electromagnetic waves, but here we use seismic waves.
Silicon and oxygen, we need a very large amount of energy, which is not economically feasible. So that's why we don't use these pods for extraction of silicon.
Very strong bonding.
Strong bonding between silicon and oxygen.
Difficult to extract.
To separate silicon and oxygen, so it's very difficult to extract silicon from it. But still, it have uses. We can use it for in many industry, like it's used in I think some maybe cosmetics or something. I'm not sure, but it has many uses.
This is lab of feldspar.
This is a feldspar, yeah. This belongs somewhere in between these two end member. So it has sodium and calcium both in it in this member. It has means like its primary use is can be used in making floors or something like ceramic industry. But this can get converted to a secondary mineral, which can be used for economical extraction.
Laboratory feldspar.
Laboratory feldspar.
It's formed for the magma. For instance, here we have this is the igneous rocks, and this is sedimentary, and this is metamorphic, and then the rocks cycle continue. So if the rocks are here, like this one is granite, this is plutonic one, and we believe the silica is around 65 and more. So if it's formed on the very deep of the earth, we call them plutonic, and then if it's formed in the intermediate, we call them intermediate, and then if it's volcanic on the surface of the earth, we call them volcanic. For instance, here we call them rhyolite. And if the silica it's become less, like 65 to 52, we call them intermediate. For instance, this is the cyanide and this is the trachyte. So the cyanide and microcyanide same as granite, but and the volcanic one is called trachyte. So when in case of the the continent, when we came to the ocean and then we came to the mafic rocks, we call them mafic. For instance, the silica will be around 45 to 52. So the gabbro is example of the mafic rocks. So if it's formed intermediate, gabbro is plutonic one. If it's intermediate, we call them dolerite. And then from the dolerite, we have the volcanic one, and we call them basalt. Now there are two types of basalt. Either it's formed on the, because Earth either it's in the ocean or it's either on the continent. So if it's formed in the continent, we have this type of basalt, but if it's in the ocean, we will call them below lava basalt or below basalt. And this is how do we know it's in the ocean? When we see this vesicular, can you see those vessels and those bores? we believe this is escaping
Oh,
of
the
the
air
gases.
escaping from
Yeah, as gas escape from here. So this one from Chitradurga here in Karnataka, and they've been dated through the Geological Survey of India and through a different method of dating. The age is 2.5 billion years ago, which is almost half life of the Earth. We believe it could be life existing since that time, but still needs some more analysis to be done. So now, if the rocks are left from here, some material left from the magma, we will give you segregation. We call them dunite. But if the rocks form directly from the mantle, we call them hasbergite. So this is collection for our Professor Saif. You have them directly hasbergite, so it's very lucky to have. Moreover, as I shown you before, this is a comatite. You can have comatite, as you've seen. This is equivalent volcanoes, so equivalent volcanoes for the mafic. This is ultramafic. The silica here is less than 45. So the comatite is good for the diamond. You can have diamond on this rock, so don't take it back again, okay? So we believe
diamond mines, you find a lot of comatite.
Yeah, if you need to, you can have the comatite, you can have it for diamond mining, and also along with the kimberlite. But the difference is here, the diamond is small pieces, not like kimberlite one. Okay. So this is the typical mantle rocks. You can have it from this ophiolite from Oman, and this is from Japan. Also the rhyolite from Japan, where the collection is. So think of these rocks as having a pressure and temperature around 800 degrees and more. So when they came to the surface of the area, they have to adjust with the new environment, so where the temperature and pressure are different. So they have to scatter, they have, again back. If the rocks are instantly cooling into the surface of the earth, we will have obsidian. That's why if you can touch it here, it's very smooth and very shiny rocks, so it's glassy material because of the instant cooling of the volcanoes. So if you have seen this before, or it's rare to see, when volcanoes start erupting the material and pushing the material into the atmosphere, you will have this kind of lapilli, and rare to get. It's not
They
always.
cool literally in the air and they fall down
Yeah,
to the earth.
literally in the air, and then you can touch them. It's look like these pieces.
Popcorn, dude.
Yeah. Make sure to return it back. It's more expensive and more rare and needed. Okay, now think of these rocks are formed under 800 degrees temperature when they came to our Earth's surface with a very low temperature, even low or minus. So what will happen? They have to scatter, they have to smash, they have to adjust with the instant change in the environment. So what will happen? We will have them in the pieces. We call them sediments. Now the sediments, they move under different kind of transportation, either in the can be the gravity, or can be the wind, or can be carried by water. Based on what we have, either we have the continent, they can go to the continent where the low land area, they stick on it, they stay. Example, we will have a sandstone, example of the continental. If they go to the ocean, we have a shale and limestone, where the limestone we believe we can have, if we take it into the, we got lots of animals and lots of something that's life on them. So that's one, if you have, imagine if you have a trough and then you accumulate some material and then you keep adding more and more and more, what will happen? Pressure increase and the temperature increase and the load increase. What will happen to the one in the bottom? Will start adjusting with the new environment and the new change of the temperature and pressure. Then what will happen? We will go back, we will get our new friends of the rocks, we call them metamorphic rocks. And these metamorphic rocks, we will believe, started by the slates, where you cannot see really with your eyes, but we're believing that there is some change in the composition because of the pressure and temperature and the load that's affecting on it. So what will happen? We take this to the microscope and look at it down in the microscope. Here, my friend will show you how it looks like. You will see the minerals start deform, because if you look there, you see the minerals, they have different crystal, they have different shape and mode of occurrence and birefringence and all. When they change that one, it means we have changing their pressure and temperature. Now, we're adding more pressure and temperature. We go to the second stage of the metamorphism, we call it phyllite. If you can see here, there is slightly some layering and some kind of schistosity or some kind of arrangement on the line. You add more pressure and temperature, you start seeing from far like the schist, here it looks like a piece of like a glass material, or if you could see them like a layer, small one. You could, it's very clear. You can see it. Back together, you can see it. Yeah, you can see the line, right? But from here, you cannot tell me, okay, this is the black mineral or white mineral, unless you come very close. Meaning that you are in temperature and pressure, but it's still slow and still not that much more. So if you still have more pressure and temperature, you will get a nice rocks. So this we call them original metamorphic rocks. So from far you can tell me, okay, there is banding here for the light minerals, for dark minerals. So the minerals start forming each together, start segregation, and start arranging themselves, the black one and the white one together. So this is one we call them high metamorphic rocks. Now think of if we have a question, can we get a minerals, either in land or in the ocean, that's made, can make a rocks? Can we? The question from the geology and the answer also from the geology is the same. Have you seen marble? The marble is made of one single minerals. We call them calcite. So this is made in the ocean. Again, also we can have a monominerals rocks, metamorphic one. Let's call it the quartzite, made mainly from the quartz, which is metamorphic rocks. So we believe again, we add more pressure and temperature, the rocks goes back again to our friends here in the magma, and then start melting the rocks, and then start erupting and cooling in the different rate of the degree, in the plutonic, intermediate, and the volcanics, or even faster, instant cooling of the obsidians. So if you want to see, you can see on the microscope here, my friend will show you how it looks like, or more metamorphic grades here on the fascies, will be explained here by my friends. So thank you. Any question? And then remember, if you have your dime. Yeah, welcome. Thank you. Thank you very much. Thank you. Yeah, this is a collection.
From a magma, and these are all metamorphic rocks. Metamorphic rock means pre-existing rock is subjected to pressure temperature conditions and it transforms to a new rock. And we have this diagram is known as metamorphic facies diagram. Each rock is made up of minerals, and each mineral is having its own pressure, temperature, stability field. So according to that, we have different facies over here: zeolite, prahanite, pumbleite, green schist, amphibolite, granulite, blue schist, eclogite, etc. So the zeolite group of minerals, which is having a comparatively lesser temperature and pressure, like 204 kilobar pressure, this is a zeolite mineral known as scolecite. Okay, and these are hornfels, rocks known as hornfels, which is formed at contact metamorphic zones. You can see over here the contact metamorphism means when a magma comes in interaction with a host rock, it transforms the host rock to a new rock, and thus the hornfels forms. And these are the medium pressure rocks called green schist and amphibolite facies. The green schist facies got its name because it has a green mineral called chloride, and the amphibolite facies is having amphiboles as minerals, mineral assemblages. So these are ultra high temperature rocks, which is having a temperature range greater than 900 degrees Celsius.
You can see the different rocks that's actually fused
Yes,
together.
yes. This is garnet, a mineral called garnet, and you can see the same mineral over here, but the size is smaller. And the temperature and depth is different. So the mineral formation is different. So this is garnet, and the rim is pyroxene. So this whole texture is known as corona texture. Corona.
So if you were to take a cross section, you can find different rocks.
Yes, yes. Different mineral assemblages will be different. Yes. These are higher pressure, higher temperature rocks, eclogite facies rocks, and it is characterized by a mineral called omphacite. And these are formed at a greater depths, greater than 40 kilometers beneath the earth. And these are blue schist facies, these high pressure rocks. Blue schist means it is characterized by a blue mineral called glaucophane. Yes.
Do you know where I can get rocks in Bangalore? Let's say I have to build sections of the home. You know quarries in Bangalore I can source rocks from?
Yeah, Darbar Craton is full of many quarries are there. Yes, yes, yes.
Very cool.
Thank you so much. Hi. You have seen different rocks over there. Thank you.
So I can explain, or someone need to come and explain? So this is the Mohs hardness scale. This is the Mohs hardness scale. This is founded by the Friedrich Mohs. So that's why it's named as Mohs hardness scale. So this thing we usually used in the field, geological field. So we know that rocks are formed of different types of minerals. So in some way, different minerals having same color. So how we differentiate it's this. So we know that all minerals having different physical property. So hardness is one of the physical property. So these things can start from calcite to diamond. So calcite having the hardness of 1, this having 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the hardness scales starting from 1 to 10. So the basic idea is like that we can scratch the lower grade using the higher one. So we can't do it in the reverse model. So we using this diamond, we can scratch all of these minerals. So that's the basic idea of that. That's it. Thank you.
Yeah.
So this is the diamond bearing timberlite pipe from where we extract or mine diamonds naturally. So the diamonds need like high pressure temperature conditions to be formed. So the one which is formed like 250 to 150 kilometers beneath the Earth's surface is carried through the by the kimberlite pipes to the top surface so that we can mine it easily. So the kimberlite pipe, they are known as the natural elevators. They bring up the diamonds to the top surface and we can mine it easily. So in India we have Machhajwan kimberlite pipe, which is one of the most famous one, from which we like collect diamonds. And South Africa is also a world famous kimberlite, like diamond, diamond bearing country. So Kimberley was the first place from where we mined diamonds. Yeah. It's
Thank you.
So hello, my name is Homi. So I am a second year PhD student here at the Center for Earth Sciences. So here I will show you two different type of metamorphic rocks, how it looks under microscope. So here I choose two extreme type of metamorphic rocks. One forms at very high temperature and the other one forms at very high pressure condition. So how we make this thin section? We take the rock, we make a chip out of it, then we polish it, then we stick it on the glass slide. Then the top surface, again we cut it and do the polishing till diamond. We need our surface to look like mirror finish. So this is a very high pressure metamorphic rocks. They form at the subduction zone. You know the plate techniques. So one plate is going below and the one plate is going up. So at that subducting slab, downgoing slab, you will get this type of rocks. This is a eclogite. More than 2 to 4 gigapascal pressure it suffers. Now this is a ultra high temperature granulite, UST granulites. So they represent temperature more than 900 degrees centigrade. Like we say it based on the presence of specific mineral assemblages, which is called sapphirine and quartz. Now I will show you how it looks like under microscope. Yeah, you can see. So there is a small tiny blue dot in that you can able to observe this. There is a small tiny blue grain. Yeah, and also inside it there are like blebs. Yeah, so those are quartz, those are SiO2, and the blue colored mineral one is your sapphirine. And in which it is existing, like the bigger grain, that is garnet, the lighter pink color. Okay, so if sapphirine and quartz, they are coexisting together, you can say that, okay, this rock forms at temperature more than 900 degrees centigrade. So this is like a characteristics rock of ultra high temperature metamorphism. So now I will show you this how high pressure rocks looks like. So there is a small rounded grain, like this is a light pink color, light reddish color, that is garnet, and surrounded by there is a green colored mineral, right? Yeah, that is omphacite pyroxene. So it's only stable at very high pressure. You can only get these minerals in these high pressure rocks. So these are characteristics of your very high pressure metamorphism rock. Temperature is not that high, but the pressure is really high, around 2 to 4 gigapascal or more than that. So these are the two extreme end members of metamorphic rocks, and you can see how it looks under microscope. Yeah. Yeah, thank you.
So this is the Continental. So this is the Continental drift, which was an idea proposed by the Alfred Lothar Wegener. He was a German meteorologist with no background of geology. During World War I, he was injured. He was a German soldier. He was hospitalized and he was bedridden while he saw his friend holding a map. And that pointed on him these two continents, Africa and South America. He thought if you put together, it fits perfectly. So he thought maybe in some point of time, the all continents should be together. That's how he came up with Pangea, a C alphabet C-shaped supercontinent, which is known as Pangea, and around that there is a single ocean which is named Panthalassa, which was during Permian period 250 million years ago. And after 50 million years, during Triassic period, this Pangea started to split. And the upper portion, which contains North America and our Europe and Asia, by this time India was not the part of Asia. This is known as Laurasia. And the bottom part, which is known as Gondwana, which contains Africa, South America, Madagascar, Indian plate, Antarctica, Australia. Indian plate was also attached to the Antarctica and Australia, but by the late Triassic, Indian plate started to move away from Antarctica towards Asia. During Jurassic, South America also started to move away from Africa, and Australia also started to rip away from Antarctica. And Indian plate reached middle of its path, and during Cretaceous, the Australia moved away, and Indian plate was near to collision, and Cenozoic, the present condition, the Indian plate collided to the Asian plate. The collision caused Himalayas to form. When two continents are collided, mountains are built, which is known as orogeny. That's how Himalayas are formed. Himalayas are the youngest mountain ranges, which is still growing. Why? Because of the Indian plate is pushing towards Asian plate. That's why Himalayas are still growing. Similarly, in the ocean, what we see is above the surface, and in the ocean, there is also something similar. The oceanic crust, when two oceanic crusts collides each other, the denser one will go down. Why? Because of there's where seafloor spreading comes, like in the Pacific, mid-oceanic ridges, when the lava comes up and it solidifies, basalts are formed, and repeated process causes the plates to push. And at the tip, the Pacific Ocean crust is going downward, where Mariana Trench are formed, and gradually the tip will reach, will get molten, and it will again form lava, which will repeatedly comes through the ridge, and this seafloor pushing will get continuously. So you can't find any older rock in the oceanic crust, but you can find older rocks in continents. Why? Because of the seafloor spreading. The older one will go eventually at the tip and go the trench and get molten. And Wegener had evidences to prove the splitting is happen. Like in South America and Africa, he found fossils of a freshwater reptile named as Mesosaurus. So currently there is a mid-Atlantic Ocean. So it is a fresh, as I mentioned, it is a freshwater fossil, a freshwater organism. It can survive in salty water. So that also pointed to a single continent like Africa and South America was joined. And also in Ghana and Brazil, there is gold placer deposits which have similar characteristics and age. And also the third one was the jigsaw puzzle pattern, and the fourth one was like paleontology, geology structures, mountain ranges, as here you can see the Appalachian Mountains in North America and Caledonian in Europe. If you put together, that will be continuous, and their rock formations are also similar of age. And in Himalayas, we can find the remnants, also the marine fossils of DESE, which was found in between of Gondwana and Laurasia. Thank you.
Okay. Yeah.
So,
our first introduction is named.
Okay.
Okay, one talk about it.
Yeah, sure. Hi, I am Ruby. Okay, sure. Yeah. Yeah, hi, I am Rubina. I am explaining the mineral and rocks here. So when we talk about minerals, so as we naturally know that zinc, in foods we have different type of minerals like zinc, copper, iron and calcium, phosphorus. But in geology we don't tell them as minerals. So we call them as elements. So when they are forming a particular substance or particular elements, like calcium is forming calcium carbonate, like CaCO3, it is calcium is the cation and CO3 is the anion, and they form a mineral. So when they form a substance, we call them as a mineral. So here you can see that is a calcium carbonate and they have a particular structure. So we call this a mineral, and when they grow in a very low temperature and they grow very beautifully because based on the thermodynamics they have a very low surface area, and so because of that low surface area they have grow very bigger. Their crystals are very bigger and they form very naturally, they are formed a very beautiful crystal structure. So it is the pure calcium carbonate, and if we come to this mineral, this rock, it is mainly SiO2. So in this SiO2, mainly when we talk about quartz, it is transparent and there is no fracture, no cleavage and all. So but here, because when we talk about crystals, crystal has lattice points, right? So when there is any defect or anything which is like coming because of any defect, any forming mineral element is coming out to back in to remove, like how can we to complete the vacant space, other minerals which is present in the system, they incorporate in the mineral. So because of incorporation of other cations in that system, they create a color. We call it hue. So if we see in that mineral, it is purple, it is pinkish. So because if we the pink, how, so the first question comes, how the pink color comes. So pink color comes because of the titanium, Ti, which is called Ti. So when SiO2 removed from the lattice, the Ti take place of the Si and they create a color of pinkish. And if we can see, there is a other variety and it is purple, and because of the incorporation of manganese, Mn, it is create a purple color. And there are and it is azurite. Azurite is a mineral which is forming because of the Cu or copper. So there are many, and here is another. So here you can see another calcite, which is a twinning, which showing a tuning. This is mineral is this specimen is perfect for twinning, and then comes the question, what is twinning? So twinning is majorly a feature when the minerals forming, they have a tendency to grow together simultaneously. One or more than one mineral crystals forms. So when they intervene with each other according to the any plane, so they are called twinning because they are growing simultaneously with and they are intergrown. And so I can show you a cutting sample, and here you can see how beautifully it was intergrown. So here is a crystal structure and there is another one. It is majorly crystal, a crystal of calcite, and this is a pink quartz. So, and if we talk about then now it comes how the rock forms. So when there is aggregates of rocks or aggregates of rock minerals, they form together and they form a rock. So now we can come to a rock. So if we see that this is a black mineral and this is a white mineral,
The black, when we see in nature, the black mineral, they form first because of they are rich in FEMG. So they form the mineral which and they, when the magnesium and iron for just finished in the magma, then the other minerals like sodium rich, potassium rich, calcium rich mineral forms, and they are the whitish part. So this is a manganese or magnesium iron rich, and this is a sodium potassium rich, and it is a aggregate of two minerals which form a rock. So, and this one is a hematite. As we know, hematite is a rock of iron, so it is a Fe2O3. So when we process it throughout our what to say, in our industry basis, we can get a iron or our steel from this hematite ore. And you can see there are several rocks, and that is a pink quartz. Okay. And if we talk about rocks, there are three types of rocks. One is because of magma, one is because of when the pressure temperature changes, they became some metamorphosed rocks, and there are sedimentary. When they eroded, they come to the through the river basin or wind through the to the ocean, and they form a sedimentary rock. So I can show you a. So it is a igneous rock. You can see the crystals here, and it is mainly a dolomite, crystalline dolomite. It is a good example of igneous rock, and I can show you an inside here. I can show you a sedimentary rock. It is a sandstone. It is a calcareous sandstone, and you can see those are fine grained because of the erosion, because they are fine and they form a layers of rocks, and it is a very good layer, and we can see it is formed in the ocean bottom, and we can see because of the compaction we get a sedimentary rock. And if we talk about, so here we can see those are the low temperature metamorphic rocks. Those are formed because of the pressure temperature changes, and when the magma comes to the subsurface, they are just create a very beautiful structure, and those forms, and those are the majorly cut and polished samples. That is why they are beautiful. So thank you so much. I think it is fine.
Okay, so what we are showing is the evolution of life here. Okay, so from 3.5, 3.6 billion years ago till the present day. Okay, so I've divided the entire thing into Precambrian and Paleozoic, Mesozoic and Cenozoic. So what is Precambrian and Paleozoic? It ranges from 3600 okay, to 500 million years ago, 3600 million years to 500 million years, and we have the earliest forms of life in this. So what are the earliest forms of life? We have the stromatolites. Okay, these were organisms that could live even without oxygen. Okay, the very fast organisms on Earth, and apart from that, they kind of existed till and they were soft-bodied organisms, no hard body parts were there. So hard-bodied organisms started coming up after 500 million years when we got the Cambrian explosion. Yeah, so 500 million years start from here. Yeah. So there you get the hard-bodied organisms. So this one particularly it is called brachiopods. Yeah. But mind you, they are all marine organisms. We yet have not come to the land. Okay. So after that, coral and plant. Yeah. So you have seen modern day corals as well. This is a coral back from 450 million years. Okay. Again, marine, not yet we have come to land. So to come to land, we have to come to Mesozoic. Okay, no, not really, because the first land plants arrived in around Silurian, which was a part of the Paleozoic itself. But more prominent ones in Mesozoic. Mesozoic is pretty popular, you know, because of Triassic, Jurassic and Cretaceous. So unfortunately, I don't have dino fossils with me right now, but I can show you something tempting. That is the gastropod remains. Gastropod. The modern day equivalent of yeah, I'll show you more, and these are just how they are preserved. You can see the coiling. Yeah. Apart from that, a very important role was played by cephalopods. You have heard about ammonites? Yeah, so cephalopods, where you can think of them as ancestors of modern day, you know, prawns and so. So the soft body thing, they didn't get preserved. Only we have the hard body, you know, remains of the hard body that we get as fossils. So again, this one. This is the hard body fossil that is remaining, and this is a much clearer view, I think. You can check. And just to draw your attention, they were kind of the fastest moving organisms at their time. Okay, and apart from that, we have belemnites, which might not look very interesting, but it is interesting because they were kind of finger-like cephalopods. Like first, these they were also marine organisms, but they were typically a very finger-shaped thing. So after all these things, we get the dinos. Dinos get extinct in 66 million years back. So from 65 to 66 or so till the recent day, we have the Cenozoic. After that, no major mass extinction has happened, so we are still living. So I'll just show you modern day baby shark teeth. Modern, but it's a baby shark teeth. Yeah, okay. And I would like to show you a modern day starfish. Yeah, and I can show you a modern day coral as well. So you might be thinking what these people are doing with these things. It's pretty good to look at, but what's the use of it in science? So use of this in science is all of these things are proxies for us, because what we do in our studies is we, apart from the evolution of life that is being studied, we kind of try to know the paleo environment, the paleoclimate reconstruction that we try to do. So yeah, because think about the shark that is living in today's ocean. It is drinking water, taking nutrients from today's ocean itself. So whatever signatures, chemical signatures that the ocean will be giving, ocean water will be giving, that will be stored in this as a you know, as a signal, as a geochemical signal. So what we do is we do isotope analysis of these kind of specimens, and we try to know, say, what is the geochemical signature of ocean water at today. Similarly, if we go back till stromatolites also, now because we know it formed back in 2500 million years, 1900 million years. We can do geochemical analysis of this particular one and we reconstruct the climate of that time. Say what was the, like we usually do carbon isotope analysis, oxygen isotope analysis. Carbon dating you can't really do on these samples because carbon dating has a very, carbon 14 has a very less half-life. Yeah, so you really can't go back to 2500 years or 1900 years. No, you can't. So, yeah, these cannot be subjected to carbon dating, but these are like pretty good proxies.
ಇದು ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಲಾ ಒಂದೇ ನಿಮಿಷದಲ್ಲಿ ಇಷ್ಟೇ ಅಲ್ವಾ ನೀವು ಸ್ವಲ್ಪ ಕ್ಲೋಸ್ ಬರಬೇಕಾಗುತ್ತೆ ಇದರಲ್ಲಿ ತೋರಿಸ್ಬೇಕಾಗುತ್ತೆ ಹಾಂ ಇಲ್ಲಿಂದ ನೋಡಬೇಕು ಹಾಂ ಹಾಂ ಸರಿ Hi, good evening. My name is MD Nasir Hussain. If you could observe these minerals, these are called as fluorescent minerals. So what they do is they will show the luminescence. So in this magic box, we have kept a UV light. What does UV light do? UV light is a very high intensity and high energy light. So when we keep the minerals inside the expose them to UV light. Yeah. So the minerals, crystals will observe the UV light radiation, because of which the electrons inside the minerals goes to a higher energy level. So because of that, what happens is, after they go to higher energy level, they will come down to lower energy level. Because of that, what happens when they absorb the UV radiation, whichever the UV radiation that they have absorbed, that will be emitting as a luminescence. Now the camera will come and show. Flash off madi. So if you could see the UV light inside, there are crystals that are glowing. Crystals are glowing inside. So this is the luminescence effect. This is happening because the heavy radiation that the UV light absorbed, the crystals absorbed it. So those, after it came to the lower energy level from the higher excited energy level, this is now emitting the luminescence after it comes back to the lower energy level. Thank you. Gaming.
1 minute reduction. Yeah.
I am a PhD student in Center for Earth Science Department. So today in our open day, we are doing a fossil finding game. So this is a fossil finding game. Inside the sand, there are fossils are there. You have to find one fossil and draw it there. Just you have to take a look there. Then find it one. So this is bivalve only. This is made of calcium carbonate. This is found in ocean. Okay. So you just have a look, observe, then draw it there. Observe. Any place. as a gift for you. Okay? That's it.
So, hello all, my name is Shivesh. I am from PhD second year student of Department of Earth Science. I am doing PhD under the Professor Prosenjit Ghosh sir. So now we have discussed about the rare earth element and critical minerals because in now the modern era, the machinery and other like EVs and technology are came. So we have used some like this is the rare earth element. This rock is called pegmatite. So in this rock, one mineral is called lepidolite. So the in lepidolite the lithium concentration very high. So we extract the lithium and make a battery to put in the phone and or EV. And this is the apatite. This is also a minerals for rare earth element. And this is zircon. This is for nuclear energy. Suppose the coal is got extended, so the new era came is called the nuclear era. So we have produced energy from the uranium, thorium, and the second sector is called the critical mineral. That is very useful for our country because every country fighting each other for taking the critical mineral like China. China is very very big reservoir of rare earth element. So this is called hematite. This is very enriched rock of iron content. We have extract iron and make a daily like things like window, iron rod and all things. And this is chalcopyrite. You can see here. This is the glowing part or gold like things. This is the ore of copper. So we can extract copper from here. You can see the copper wire, and this is also a copper called azurite. This is the ore of copper, and this is called the pyrite or fool's gold. This is the iron sulfide formed in a reducing environment, and this is very useful for critical minerals. And this is lodestone of manganese ore, and that all. So आने वाले समय में लोग इसके पीछे ज़्यादा भाग रहे हैं क्योंकि आने वाला जो एरा है वो रेयर अर्थ एलिमेंट और क्रिटिकल मिनरल पे ही बेस होगा, क्योंकि वॉर में भी जो यूज हो रहे हैं, वेपन्स बनाने में यूज हो रहे हैं, न्यूक्लियर एनर्जी आ रही है, टेक्नोलॉजी आ रही है मशीन बनाने में, तो हम इस मटेरियल का यूज़ कर सकते हैं. ओके, थैंक यू सर.
Keep it in this and speak.
So my
Speak this.
she will also be speaking.
Kidra, angere.
How we will like to. मत करो यार. या अबे रुक जा. नहीं बनेगा ये नहीं बनेगा. Okay, so
Hello everyone, we are from GRU lab, and here we are showing how we can make instant ice cream using liquid nitrogen. So what we are doing here is we are taking a batter, ice cream which is made up of milk, and we are adding liquid nitrogen to it. Add.
The ice cream we are making, it doesn't constitute any ice. We are freezing it by using liquid nitrogen.
And the temperature of liquid nitrogen is minus 196 degrees Celsius. So what happens here is there is an instant heat transfer,
and hence there is a rapid cooling of the premix,
which solidifies the liquid. So we got the instant ice cream.
You may also taste the ice cream. Somebody,
if you want to taste, you can come and taste. Tirtha, tu hi aa jao.
Well, it's good.
Okay, so this was all.
Yeah. Okay. Hi. So we are kind of trying to estimate the mental viscosity with help of glacial-isostatic adjustment. So we'll start with a very basic. Earth is made up of different layers. The top part is crust. Below we have mantle, and below that we have outer core and inner core. So we are mostly interested in to know about the Earth's mantle. So we try to understand how the process inside the Earth mantle kind of affects the features that we see on the Earth's subsurface, like mountain formation, continental drifts, new ocean formation and stuff. Because we cannot go inside the mantle to see what its physical properties are, we find alternate ways to kind of estimate its physical properties. One of the method is to look at glacial-isostatic adjustment, and using this GIA, we are trying to find out the viscosity of the material. So first we'll go through what GIA is. So basically glacial-isostatic adjustment means adjustment is due to the formation of ice sheet. As the name suggests, the glacial means ice sheets. So over the period of Earth's history, there has been various cycles of formation of ice age on the Earth's surface. So with the time, Earth has been heated up, cooled down over and over again. So when Earth heats up, cools down, it forms ice age, and when it heats up, every ice melts away. So the last period of ice age was 10,000 years back in the time, and we'll show you a demonstration how this formation of ice age kind of deformed the Earth's surface and the mantle below it. So when ice forms, it keeps on getting accumulated on the Earth's crust, and it kind of deforms the Earth's mantle. So if we can kind of relate it to the cross section we see here, wherever the load is, which is this part, it will gonna bulge, it gonna get depressed, and the periphery is gonna have a bulge around it, which is kind of same what we are seeing here. The fluid's gonna move away from it. As we know that again Earth's gonna go in heated period, that means this ice gonna melt away. Now when ice gets melt away, everything gonna come up due to the pressure being released. When the pressure is being released, again the fluid will come back its in original place. Now this will lead to an upliftment over here, and then the things will go down on the sides. Now this is how the whole process takes place. But how do we know, how we observe this phenomenon on Earth's surface in present day is what we see using GPS. So when we use GPS, we get the vertical velocity of Earth's surface. So this is the present day vertical velocity on Earth. all these red areas that we see are undergoing an upliftment, and the blue areas that we're looking at are going down, which is kind of very true to this. See, center is coming up and the periphery is going down, which is very kind of related to this. So we are kind of intuitively says this is the reaction what we are looking at up here, and it's also kind of a similar area where ice sheet was present in the past. So now if you think about it, the ice age was 10,000 years back, and we are still seeing the consequence of it in the present day Earth structure, and this kinds of give you an idea how high the viscosity will be of Earth's surface. And using some mathematical relation and physics, we get an equation which kinds of relates to the upliftment rate to the viscosity, and using this upliftment rate from GPS data, we can get a viscosity of Earth's structure. This is one of the present day method to do it. There's alternate methods to do which can help us to get an idea how things are happening in the past. Those are the geological evidences. So if you look over here, this is one of the area which is very close to where the ice sheet was. So basically the concept is, imagine this being the crust, this being the sea level. So when the crust is coming up due to the rebounding, it seems like the sea level is kind of falling over time. So now if we look here, it just seems like with the time sea level has gone down, and as the sea levels goes down, it kind of erodes the area next to it in a pattern, and when we do this geological dating of it, it kinds of tell you the rate of change of the sea level. And when we plot it on the Earth's in a graph, so here this is back in time, which is 8,000 years back, and this is present day, and we can see there is a change in sea level, and with time it has, okay, this will change, it will go back, it kinds of goes down with the time. And when we use our viscosity values and the basic model concept, and we apply those to understand the nature of the mantle in the past, we get similar kind of results. So this solid line is what we model, and which kind of fits the data very well. So it's kind of tell us how mantle behave over the time and what would be the viscosity of the Earth's mantle. Thank you.
मेंटल को अर्थ स्ट्रक्चर बोल देते हैं, विस्कोसिटी ऑफ अर्थ स्ट्रक्चर. You don't need the mic. Yeah, wait. Take a mic.
Like.
Oh, अच्छा. So here in my experiment, I am showing a large ocean scale processes in a smaller scale. So what happened is, if you consider this side is land and this is the ocean, so when wind blows from land side towards the ocean side, it drags the surface water towards the ocean side, and because of that, this deeper color is representing the deep ocean water. So as the surface water is dragging by the wind this side, the deeper oceanic water is coming towards the coastal side, and the deeper water is nutrient enriched. So in the presence of sunlight, it's increasing the productivity. This process is called surface upwelling. It helps in fishery and other processes. So that's it. She will explain some more experiments.
So here,
So here we are showcasing some foraminifera. These are the microfossils, and these are the calcareous shells. They live in the ocean. They have different depth habitat, and when they are living, they are forming their calcium carbonate shells from the seawater. And what they do is they record the ambient seawater conditions like the temperature, salinity, pH of the ocean. And once they are dead, they sink to the bottom of the ocean floor. And what we paleoceanographers do is we collect the sediment cores, that is we sample the sea floor and get the fossil fraction separated out from that sediment and study these calcareous shells. So we study various chemical tracers like boron isotopes, trace metal by calcium ratios to understand how the temperature, how the pH of the oceans have evolved through time. And these marine organisms are quite a faithful record, like archive of seawater, and helps us understand the past climate. So this is a picture of a living foraminifera you can see here, and here we have tried to show the depth dependent habitats of the forams that are present in the ocean. Then it's a slide showing how we chemically process our samples in our lab. And these are the images of Southern Ocean expedition where we collected the sediment samples from the ocean floor. And this is how the water sampling is done using the Niskin bottles in the Southern Ocean. This is how, so these are the sediment cores from where we actually separate out the fossils and we study the past climates. So these are the analytical facilities available with us in our lab, and these are the instruments in which we analyze our samples. This is just a methodological framework of how we process our samples in the lab. And that's it. So these are some of the photos from Southern Ocean expedition that took place last year, and I was one of the participants on it. Thank you.